Okay, I think it's live now.
Yes.
Okay, thanks, Nika and everyone. Yeah, I guess we can get started. Let me actually also get to my screen over here. Okay. Okay, can you see the screen well? Okay.
Yes.
Okay,
Yeah,
good. Okay, good. Let's get started then. Well, hello, everyone. Welcome to our lecture 17. I was hoping to give this in person, but I'm a bit under the weather, and I certainly don't want to be a health hazard. So we're going to do this online, unfortunately, this time. Let me try to make sure I don't hear myself over here. For some reason, I'm hearing myself. There's some echo. Okay, I turned that off. Okay, so today, remember last week we had 2 lectures on cutting edge research in computer architecture. Hopefully that was exciting. I got good feedback from several of you on that. Did people like that? The research lectures? I hope so. Okay, today we're going to continue where we left off the previous week, which is emerging memory technologies. And we're going to start parallelism and heterogeneity. We're going to kind of take a different turn in the lectures and talk more about multiprocessing, accelerators, etc. in the remaining parts of the lectures. So hopefully it's going to be fun. But first, we'll finish emerging memory technologies today. And again, feel free to ask questions. I hope I will be able to hear you when you press your button and say something like we did in the past. So feel free to keep being engaged today as well. Okay, so let me just give you some reminders. We were talking about emerging memory technologies, and we covered a lot actually emerging memory technologies in one lecture. And we talked about phase change memory, for example, as an example, emerging memory technology that is quite promising to potentially replace DRAM. We talked about challenges in phase change memory in terms of its using it as a DRAM replacement, but people are already trying to do it, as we discussed. But there are significant challenges in terms of latencies, especially write latencies, but also read latencies, as well as energy, write latencies especially, and endurance, which is a problem that DRAM doesn't have as far as we know so far. So it's not easy to replace DRAM technology with phase change memory, but it's a good research topic to try, certainly. And we discussed some publications. We're going to discuss some more. And we also discussed that this is already happening today, basically. We already have memory modules that is made of phase change memory called 3DX point today. And you can use this in your systems. And as we discussed last time, these are already reasonably low cost. So you can get very large capacity memories at low cost, but the memory may have some undesirable characteristics, of course, compared to DRAM, like we discussed. And we discussed some papers that introduced the topic, tried to replace DRAM with phase change memory. We discussed other papers that try to do more. Okay, there you go. And we discussed some papers that also try to take advantage of asymmetry in the read and write latencies of different bits in phase change memory, for example, to improve performance. By the way, this sort of asymmetry in read and write latencies actually exists in flash memories as well. So whenever you have multi-level cell technology, some bits become easier to program than some other bits. We discussed that, for example, the most significant bit becomes easier to determine in phase change memory compared to the least significant bit if you have 2 bits per cell. And that's true for flash memory as well. So you can actually improve performance as well as energy efficiency by taking advantage of this asymmetry in reads and writes. And since we've been talking about asymmetry in our lectures, it's good to think about the asymmetries that we see in our systems, especially emerging memory technologies, and how to take advantage of them. The next part of this lecture is going to be about parallelism and heterogeneity. I will make a big case for asymmetry, if you will. And this is one example of asymmetry that makes sense to exploit in systems. Whenever you see asymmetry in terms of latencies due to some technology, it's important to design your mechanisms to take advantage of that asymmetry. For example, memory controllers or page mapping mechanisms. And this paper that I flash over here that we did not really talk about in detail talks about how to take advantage of it. And I'm not going to go into the details since we don't have a lot of time. We also discussed some other technologies that are potentially useful as well, like STT-MRAM, And this is actually also a very interesting technology, as we discussed. It's potentially more interesting than phase change memory because it doesn't have the write latency and read latency. Oh, sorry, it doesn't have the read latency problems that phase change memory has. Also write latency problems can be solved as well because write latency is a bit easier to solve. But unfortunately, as we discussed, the current cell size of magnetic memories are quite large. As a result, it may be a long while until this sort of memory technology replaces DRAM. But this sort of memory technology can be actually very good for replacing large caches, for example, large last level caches, so that instead of having power hungry SRAM and large SRAM cells, you can have a much more energy efficient STT-MRAM cells, and then you can pack many more of those so that you can get much larger cache capacities. And that's an area of research that's being pursued right now also in systems. Okay, and then later we started talking about hybrid main memory because we were not fully convinced, if you remember, that we can completely replace DRAM with one of these technologies due to the downsides of the technologies. But if you have a hybrid main memory, now we can actually design the hardware and the software to manage the data allocation and movements such that we can achieve the best of either of the technologies that we have. And again, hybrid doesn't mean only 2 technologies. It could be 3 technologies, 4 technologies. It could be different types of DRAM as well. It could be different types of phase change memory. As a result, this opens up a huge space, design space of an exploration space that can enable us to scale up memory to very large sizes, as well as memories of different characteristics, so that we can actually hopefully achieve the best characteristics of each technology while avoiding the worst characteristics of each technology, such that we can have a very large and scalable main memory in the end. Of course, this is easier said than done because managing these multiple different types of memories is not that easy, as we have started discussing in the last lecture. And we started discussing, for example, using DRAM as a cache for phase change memory. And that makes sense, I think. But again, this idea is much more general, right? You can have multiple different types of DRAM. You can have DRAM and phase change memory and STT-MRAM, for example. You can have DRAM, phase change memory, fast flash and slow flash. And then you can use all of that as part of your main memory. And this is kind of happening right now in large scale systems where we want very large memory capacities. So we're going to talk a little bit more about this in this lecture, basically. The challenge and opportunity now becomes, how do we provide the best of multiple metrics using multiple different types of memory technologies? And this, I think, brings us to heterogeneous, configurable, and programmable memory systems, hybrid memory systems, let's say. Okay, and we started discussing some issues here. We're not going to cover everything, but you can see that this has a very large space. For example, which memories should be used as cache? Which memories should be really part of main memory? This is important, I think. How should the cache be managed, for example, if you use as a cache? That's also important. What is the granularity of data movement and management? Should it be fine-grained like cache blocks today, 64 bytes, or should it be coarse-grained like megabytes and megabytes, for example, like pages today? And these have advantages and disadvantages because whenever you have fine-grained management, you need to keep track of the blocks. You need to keep track of metadata. In caches, for example, these are tag stores. And that metadata can be very large if your granularity is very small, right? 64 bytes is actually very small if you have terabytes of memory, for example. If you're coarse-grained now, you need to move a lot of data when you're moving data between one memory to another memory. So coarse-grained management may not be also very good. So it's good to enable some management that's adaptive, if you will. Whenever you need fine-grained, you want fine-grained. Whenever you can afford coarse-grained and you want coarse-grained, you get coarse-grained. But this is also not easy. So getting the best of both fine-grained and coarse-grained management in the memory hierarchy is not easy. This is actually very interesting in existing memory hierarchies as well, independent of hybrid memory systems. Today, for example, we have cache blocks that are very fine-grained, but sometimes we want coarse-grained cache blocks that are larger. Sometimes we want even finer-grained cache blocks like 8 bytes because you may have 64-byte cache blocks today, but some applications may touch only one word in it, 4 bytes, for example, or 8 bytes in it. And you're bringing this 64 bytes to the cache, even though the application is going to use only 4 bytes or 8 bytes, right? And this happens in especially random access, irregular applications today. So this granularity issue in the memory system is actually a big problem in a sense. Today, we're fixing everything. We're fixing the granularities. We're fixing the cache block sizes. We're fixing the cache virtual memory page sizes or physical memory page sizes, for example. But is there a better way to actually manage the memory systems with multiple different cache block sizes, or more flexible cache block sizes and more flexible page sizes? Today, we have multiple page sizes clearly because of this reason, but it's not flexible enough. We have only 3 page sizes, for example, in x86, maybe 4, if you look at different modes. But this granularity is very important. We're going to touch upon it a little bit, but we're not going to be able to cover it in a lot of detail. But I believe there's a huge research topic behind this that is being tackled in academia, but not maybe not enough research is being done on this topic. Okay, I spent a lot of time on the second point because I think that second point is quite important. But who should manage the hybrid memory system? Should the hardware do it? Should the software do it? Should it be hardware-software cooperative? Should different memories be managed by different agents, hardware, software, cooperative agents? This is also important again. When do you migrate data? How do you decide when to migrate data from one memory type to another memory type? Again, this depends on what's important. And this is also not easy. In my opinion, we'll see some example mechanisms, heuristic-based mechanisms. But again, machine learning-based techniques could be very useful here, in my opinion. And then also, how do you design a scalable and efficient large cache? Because the caches that we have examined so far, on-chip caches, are, if you push it 64 megabytes, for example, right? They're not on the order of gigabytes, let alone terabytes. But if you're on the main memory side, and if you manage DRAM as your cache, now your DRAM is on the order of gigabytes, right? So how do you build an efficient cache that has gigabyte level or terabyte level storage capacity becomes important, because your tag store, as I mentioned earlier, becomes difficult to manage. How do you actually adapt the eviction, promotion, replacement policies to enable terabyte level cache management is also important. And again, there are other issues here. That's what this ... stands for. But we will talk about some of these as we get along, hopefully toward the end of this first part of the lecture today. And feel free to ask questions whenever you want to. And this is where we stopped, I showed you this picture, but we didn't have time to continue. We were talking about data placement in hybrid memory. And this is an issue that has multiple facets, multiple different dimensions. I'm going to reduce it to, let's say, as small dimensions as possible right now. But at the very high level of it, you have 2 types of memories, memory A and memory B. One is fast and small, the other is large and slow. Here, we're ignoring a lot of other issues, right? We're ignoring, for example, the bandwidth, we're ignoring the endurance issues, we're ignoring reliability, but even ignoring all of that, this management is not that easy, basically. Basically, what you have is you have page 1, page 2. The question is, when do you migrate page 2 to memory A, if ever? Which memory do you place each page in to maximize system performance, basically? If you pose the problem like this, it becomes an optimization problem. And again, you can develop heuristics to solve this optimization problem, or you can develop machine learning techniques. But again, this is still a research area because it's not that easy, basically. There are multiple aspects that go into answering this question, because memories have different characteristics, and also pages have different characteristics in terms of their criticality to the application. And I'm going to show you some examples of that to help you appreciate the problem. But again, as you put more variables, like different characteristics for the memories, like endurance, write bandwidth, read bandwidth, if you try to differentiate memories even more from each other, this problem becomes even harder. So in this particular case, memory A is fast but small. And if you put everything to memory A, memory B becomes idle. So putting everything to memory A is not a good option, because even if you don't consume all of the capacity of memory A, memory B becomes idle. So you're basically wasting a lot of bandwidth on this channel. So now you have another aspect, right? It's not just about fast, small. It's also about the bandwidth that you have on the channels that are dedicated to these memories. And you don't want to load imbalance your bandwidth across these memories by putting everything on the channel A, for example, even when the capacity of channel A is enough to host everything that you have. Okay, so basically, this is the question. How should the load be balanced across both channels while also maximizing performance? And also, whenever you migrate pages, there's performance and energy overhead. These are not zero cost, right? Clearly, if you have 4 kilobyte pages, for example, when you migrate from memory B to memory A, you consume channel bandwidth here in channel B. You also consume channel bandwidth here in channel A. And you can see that the optimization problem becomes more difficult, because it's not just about maximizing the hit rate over here. It's also about how much overhead do you cost when you're migrating pages across the channels. So this needs to be carefully done, as you can see. And people have developed several heuristics for this. As we discussed in the last lecture, there was an ISCA 2009 paper from IBM that talked about using phase change memory and DRAM and using DRAM as a cache. And they used DRAM. They basically had some heuristics to place pages inside DRAM. We're going to talk about some more heuristics today that take into account. So that paper, for example, didn't take into account the asymmetry between different accesses in different technologies. But there is asymmetry between different accesses. So basically, the idea in general in data placement between DRAM and PCM is if we can somehow characterize the data access patterns of applications, we can guide the data placement in hybrid main memory. And that paper we discussed actually did some of that. But there is more, basically. So for example, if you're streaming through memory, if all you're accessing is address, let's say cache block A plus 1, A plus 2, A plus 3, A plus 4, A plus 5, A plus 6, A plus 7, and you're streaming, then the accesses that you do in phase change memory is essentially as fast as you do in DRAM, because both of these have row buffers, if you remember. And even though phase change memory row buffers may be smaller, as we discussed also, it makes sense to make them smaller, still you can manage these row buffers as a cache, and streaming accesses can be much faster in both technologies. In fact, streaming access can be as fast in PCM as in DRAM. And again, this is fundamental to any memory technology. Usually, if you're streaming through a memory, enabling high bandwidth for streaming access is easy because you can enable a large chunk of memory to be placed into a row buffer, and then you can basically get the data out of this SRAM style row buffer in any memory technology that you can imagine. It could be phase change memory, it could be SSDs, flash, for example, it could be DRAM. And so it's clearly done today in DRAM and phase change memory, and to some extent in flash as well, using DRAM caches inside the flash controllers. But basically, streaming accesses are easier to handle in any type of memory technology, which means that if you're streaming through memory, don't waste your valuable DRAM capacity, because random accesses are much faster in DRAM essentially because of the way technology operates. PCM tends to be much smaller when you access the PCM array, because PCM array is made of phase change memory cells, whereas DRAM is much faster when you access the DRAM array, because DRAM array is fundamentally much faster, as we discussed, right? Because it doesn't require these heating operations, for example, to do the writes, as we discussed. And sensing is much faster in DRAM as well due to the sense amplifiers. But basically, if you know this, you can place random accesses, that you can place cache blocks that are going to be randomly accessed, let's say, but have some reuse in DRAM. And that's the idea over here. Because random accesses can be handled much faster in DRAM, place random access data with some reuse in DRAM, place streaming data in PCM. But of course, this requires you classifying the data. Of course, if data is completely random access, meaning you're not going to reuse the page, or you're not going to reuse the cache block anytime again, it doesn't make sense to perhaps even bring any of the data from the disk, right? Cache any of the data in PCM or DRAM. And we have already seen this idea in an earlier paper. So you need to have some reuse to actually take advantage of this. So, okay, that's the idea basically. And that was proposed in this paper that I'm going to reference again. So let me quickly go over the idea again. Row buffers exist in both DRAM and PCM. Row hit latency is similar in DRAM and PCM, as we discussed earlier also. But row miss latency is small in DRAM and much larger in PCM because of the slow access to PCM array. And the idea here is to design a mechanism, either in the memory controller or the application or the software. In this particular paper, the design is in the memory controller. The memory controller keeps track of cache blocks, and it identifies cache blocks that are likely to miss in the row buffer, i.e. that they have low row buffer locality, and that are reused many times, more than a threshold number of times, let's say. And once you identify the data that have those two characteristics, you can place that in DRAM. Because the miss penalty is small in DRAM, and you want to cache only the data that's worth the movement of cost from PCM and DRAM, and you want to save the DRAM space. Basically, if the data is not used enough times, you're not amortizing the cost of data movement. You're not amortizing the DRAM space that you use, because the DRAM space can always be used for something else that is more useful, right? So the idea is to identify data that has these two characteristics and place them in DRAM, and everything else gets placed in PCM. Hopefully that's clear. And you see the reasoning behind this. And even this is not good enough, as you will see in the results, but this is better than prior heuristic-based techniques. Yeah, you can see that this is purely heuristic-based, based on our understanding of the device and understanding of the access patterns. So to be able to do that, you need to have in the memory controller some statistics store. I'm not going to go into the implementation, but certainly you can do this in the memory controller. And the paper also shows how you take into account reads and writes differently, so that you don't actually do the wrong thing between reads and writes, because writes are much more costly in phase change memory. It makes sense to prioritize writes sometimes in DRAM, as this paper discusses. The paper also discusses endurance issues, but we don't have time to talk about that. I wanted to give you the key ideas over here. Okay, let's take a look at the results over here. So the results, again, if you look at equal size PCM and equal size DRAM, these are averaged across many workloads. You can see that equal size PCM has some performance. Equal size DRAM has much higher performance. And if you manage the data using this robot for locality aware management, you get somewhere in between, which is not bad, which is better than the prior techniques, basically. But it's not close to DRAM, 16 gigabyte DRAM, as you can see. So there's still room for improvement over here so that you can get much closer to a 16 gigabyte DRAM. And remember, by actually adding some more capacity. So here, for example, the RBLA dynamic actually has 60, I believe it has 8 gigabyte PCM, 8 gigabyte DRAM, or something like that. You can actually do much better by increasing the amount of PCM in the system, as we discussed last time, right? Assuming that you can get much more phase change memory for the cost you pay for an equal amount of DRAM. Okay, so hopefully that's clear. If there are any questions, feel free to ask over here. Otherwise, I'm going to give you another idea over here. Okay. Okay, so let's keep moving on. Okay, so this is one heuristic, as you can see, and there could be other heuristics, and there are many, many heuristics. I'm going to mention some of them in a later part of the lecture. Existing solutions to memory management actually have heuristics that consider only a limited part of memory access behavior. And people actually always find out new parts of memory access behavior that can affect memory management, hybrid memory management. I'm going to give you one of the examples that we have seen before partially. As a result, ideally, we would like something that can directly capture the overall system performance impact of data placement decisions. But if you cannot capture all aspects of memory access behavior that affect performance, this is hard to do. For example, I'll give you one example. No previous technique, and including the one that we discussed, captures memory level parallelism. And if you've talked about memory level parallelism, this is number of concurrent requests from the same application when a page is accessed. This affects how much page migration helps performance. For example, if you migrate a page, you may not get any performance benefits because you may have another page that's on the critical path, as we will see right now. So let's take a look. This is, you have request to page 1, and this is in page 1 is in memory B right now. If you migrate it to memory A, request to page 1 will be served much faster. As a result, you save some time, right? That's good. This is an isolatedness. Migrating one page reduces stall time by some amount of time. And that's the time for which you reduce the stall time, right? Okay, now let's take a look at a more interesting example where we have two requests. These are two requests that are in memory B right now. Some of the requests go to page 2, some of the requests go to page 3. They're both in memory B. And let's assume that our migration mechanism migrated only page 2 to memory A. Okay, the processor needs both requests from page 2 and page 3 to proceed, let's say concurrently, to make it easier to analyze. In this case, the processor doesn't benefit. If you can see over here, if the processor needs requests from both memory A and memory B at the same time to proceed, memory B is the bottleneck. As a result, migrating only one page from memory B to memory A is not enough. As a result, the processor stalls the same amount of time, and you wasted the opportunity to migrate something else to memory A. So in this particular case, if both of these misses are serviced in parallel, then you really want to migrate 2 pages from memory B to memory A to reduce the stall time that the processor experiences. Migrating 1 page basically does not help. And you've kind of seen this before, if you remember, in parallelism or batch scheduling, right? If you have 2 requests in parallel, you want to service both of them in parallel in the banks at the same time so that you can actually stall approximately 1 bank access latency for both requests. We're seeing something very similar over here. Basically, we need these memory management policies to be parallelism aware in hybrid memories as well, as you can see. Because if you're not, then your management decision, your migration decision may be completely suboptimal. You do some migration, waste some energy and latency and bandwidth, but you get no benefit, almost no benefit out of it, because you're bottlenecked by something else, which is this request to page 3 in this case. So hopefully this is clear, and hopefully this also makes it clear that this problem is not easy to solve. And I think I've already made it clear that page migration decisions need to consider memory level parallelism. So there are some mechanisms that provide generalized migration mechanisms. I'm going to go through these relatively quickly because there's a lot that goes into it. So this mechanism, for example, that was published in Cluster 2017, directly estimates the performance benefits of migrating a page between any two types of memory. So it's very general. In that sense, it's very good. But it's still model-based. So it's still model and heuristic-based. It does a lot of modeling of the memory as opposed to machine learning-based. So I believe there's actually room for combining this sort of mechanism with machine learning-based mechanisms. So, and the idea is once you directly estimate the performance benefit, you can place only the performance critical data in the fast memory because you know which page will benefit performance by how much if you migrate to the fast memory. And if you do that, you can actually migrate the collection of pages that benefit performance by some amount, by the maximum amount, let's say, in the fast memory. So to be able to do that, it has a multiple step process. I'll go through this relatively quickly. But the nice thing is this actually works for any hybrid memory. The downside is it doesn't consider issues like endurance, for example. Once you throw endurance into the problem, it becomes a different problem because now you have another metric to optimize for. The key idea in this work is to, for each page, it uses a model, comprehensive characteristics, to calculate the estimated utility of migrating the page from one memory to the other in the system. And utility is essentially the marginal performance improvement by migrating that page to the fast memory. And it migrates only pages with the highest utility to the fast memory in this case, meaning the pages that improve the system performance the most when they're migrated. Okay, and let's take a look at the utility-based performance model relatively quickly. There's a lot more detail clearly in the paper, but you need to estimate the utility with a performance model. You need to migrate only pages whose utility exceed the migration threshold. And periodically adjust the migration threshold because this changes depending on the application characteristics over time. So how does utility get estimated? Basically, you need to have a model estimating the application's total time reduction because of migrating a page. And this provides an estimate of how much would migrating a page benefit the performance of the application that the page belongs to. You can read it also. And then you also need to understand which application is more performance sensitive to the migration. Basically, how much does the improvement of a single application's performance increase the overall system's performance? Because usually you're running multiple threads, multiple applications. And we have discussed in the past that some applications are much more important for overall system performance. Some threads are much more important for overall system performance. So you need to have a model of this as well. And basically, utility is estimated by a combination of estimation of these two metrics, essentially. And again, each of these metrics require some longer equations to estimate that you can collect dynamically in the memory controller. I'm not going to go over it, but you can read the paper for more details. Hopefully, this is also familiar because we've discussed stall time and we've discussed sensitivity sensitivity of system performance to accelerating different applications or prioritizing different applications or different threads. So we're actually using the principles that we have developed in prior works to estimate both the stall time reduction as well as sensitivity of system performance to improvement in different applications and different threads performance. Okay, assuming that you do this nicely, the performance results actually look nice, basically. So this is performance improvement compared to 3 different prior mechanisms. All means you migrate everything to the fast memory. Frequent means you have a frequency-based migration mechanism. You decide which ones are frequently used, and you migrate only the frequently used pages to fast memory. RBLA is robot for locality aware management that we just talked about before. And UHMEM is essentially the model-based management policy that we discussed, utility-based management policy. And you can see that this is depending on the workload and memory intensity, the performance improvements that you see is different because if the workload is much more memory intensive, the performance improvements are much higher. And that's basically the result. And you can see that the performance improvement is much higher when the workload is very memory intensive. Okay, and this is currently one of the state-of-the-art policies in pure hardware-based management of hybrid memories. And the good news is, as we discussed, it can work for different types of memory. And this result shows a sensitivity to slow memory latency. We're changing the activation latency and write latencies of the slow memory as a multiplier over fast memory. You can see that in this particular case, for example, on the very right, the activation latency of the slow memory is 7.5x longer than the activation latency of the fast memory. And the write latency of the slow memory is 20x longer than the write latency of fast memory. And you can see that the performance reduces, as you can see, as the latencies increases, but it doesn't reduce terribly, in the sense that if you manage the memory nicely, perhaps you can get good performance improvements overall. And again, the performance improvements of this mechanism is better when the latency multipliers are higher. Okay, so the key takeaway is this sort of model-driven techniques improve performance for a wide variety of hybrid memory systems. But again, the caveat is that we're not looking into endurance over here. So once you throw endurance, once you throw different types of reliability issues into the picture, the management becomes much harder, because now you need to take into account endurance, for example, in your model. And it becomes a not so easy model, because you need to manage both performance as well as endurance. And these really need to be managed using two different models potentially. Okay, and this is the paper that I mentioned briefly in the last few slides. So if you're interested, these will be part of your readings, and you can read it regardless as well. Okay, so hopefully I've given you some challenges in terms of enabling and emerging technologies to augment DRAM. So we're trying to augment DRAM in this case, enable hybrid memory technologies. And this requires managing your hybrid memories in an intelligent way. And again, we're not there yet. I think we need a lot more research in this area to do better and better. Let me now move into another challenge. Unless there are some questions. Are there any questions in the room or Zoom? I don't hear anything so far. Okay, please feel free to ask. Okay, then I will move to another challenge, which is designing large and effective DRAM caches. As I said, now your DRAM is very large. And if you augment it with PCM, and if you manage DRAM as a small, relatively small, but fast cache, still the management of that cache is not easy. Because you have a large DRAM cache, you need a large metadata store, meaning tag store. And you need to also keep block-based information to decide what to migrate from where. So the question becomes now, how do we design an efficient and easy to manage DRAM cache? And a good exercise to do perhaps is, okay, if this is a hardware managed cache, and if you have, let's say, 16 gigabytes of DRAM and 1 terabyte of PCM, remember, we want very large memories going into the future. 16 gigabytes of DRAM is almost nothing, right? 1 terabyte of PCM is also going to be almost nothing in the near future, because we're generating data and dealing with larger data sets. So 16 gigabytes of DRAM, let's assume that your cache block sizes are 64 bytes, right? 16 gigabytes is 2 to the 34 bytes. 64 bytes is 2 to the 6 bytes. So 16 gigabytes divided by 64 bytes is, I think, 2 to the 28. Now you have 2 to the 28 tag store entries. If each tag store entry is 4 bytes, then you have 2 to the 32. Yeah, I think 2 to the 30 bytes of tag store. That's essentially a gigabyte, right? So for 16 gigabytes of DRAM, does it make sense to have 1 gigabyte of tag store and then manage it? That becomes a bit unwieldy, if you will. Well, certainly having that tag store completely inside the memory controller becomes unreasonable, right? In regular caches, we have the tag store as SRAM, but those tag stores are much smaller. Having those tag store, a 1 gigabyte tag store in the memory controller becomes prohibitively large, so it doesn't make sense. Then the question becomes, how do you design this cache? And this is actually occupied a lot of people in recent literature. How do we actually design much more effective, very large caches? They don't have to be necessarily DRAM, but DRAM is clearly an interesting example over here, a more realistic example, such that whenever you have a load, we quickly decide, based on that tag store access, the data is in DRAM, and then access DRAM. If not, and then bring the data into the CPU. If not, we quickly decide the data is in PCM, and we bring the access data in PCM. So to be able to do that, it doesn't make sense to access DRAM to get to figure out where the data is, right? Well, it certainly doesn't make sense to have a 1 gigabyte tag store over here in the memory controller as well. So what do we do? Okay, so what do we do basically? If you want to really reduce the overhead, hardware overhead of the tag store, you put the tags in memory. But this becomes very slow. So you can store the tags in memory in the same row as data in DRAM. So if you look at a DRAM row, Now it looks like this. So this is a three-way cache in this case. It's just an example. You have the data, which is the cache blocks, and you have the metadata, which are the tag entries for those blocks. Basically, now we're storing metadata in the same row as the data, as their data. And now data and metadata, or tags, data and tags can be accessed together. So whenever you access the DRAM row, you can quickly check the tags. And basically, you can say, oh, what I'm looking for is in the same row. So that's good. Now the data access is relatively quick. You just need to have a row buffer hit. Basically, you have a row buffer miss to get the tag access and do the tag check. If the data is in DRAM, then you get a row buffer hit for the cache block because data and tags are in the same row. Okay, so that's a nice idea, I think, and that's proposed in multiple papers. I'm going to mention one of them soon. The benefit is there's no on-chip tag storage overhead right now. All of your tags can be in DRAM. Of course, the downside is now cache hit, whether or not you hit in the DRAM cache is determined only after you access the DRAM, right? You need to access the tag store inside the DRAM first, and then you need to access the data inside the DRAM. So cache hit requires 2 DRAM accesses. So we want to eliminate that. Then the question is, how do we eliminate that? The second idea kind of reduces that, basically. We're going to still store old metadata in DRAM, but we're also going to cache in on-chip SRAM frequently accessed metadata, meaning we're going to cache part of the tag store inside on-chip memory controller SRAM. And we can cache only a small amount of tags to keep the SRAM size small. And this paper that I'm going to mention shows that by only caching 8 kilobytes of tags, you can actually achieve very good performance. And that's the idea, because you have good locality in your tag store accesses. So this becomes interesting, as you can see, right? We're building a cache inside DRAM. We have the tag store, and we're caching the tags inside the memory controller because tag store is so huge. It takes too long to access the cache store inside the DRAM. So we're applying the caching concepts to the cache itself. And I think that kind of makes sense because we're already doing it in our memory system management mechanisms like TLBs, for example, and page tables. We have a lot of page table caches, for example. Okay, the third idea is independent, if you will. This goes back to the data transfer granularity that we mentioned earlier. And basically, the question becomes, at what granularity should we cache the data? Some applications benefit from caching more data at one shot because they have good spatial locality. Others do not because they're random access, let's say. And the large granularity, let's say 4 kilobytes, wastes bandwidth and reduces cache utilization. Clearly, you don't want to cache 4 kilobytes. You want to really cache 64 bytes or even lower when you have random access. And this paper proposed a mechanism to determine basically a dynamic caching granularity. And the idea is to have a cost-benefit analysis to determine the best DRAM cache block size for a given interval. I think you can do better than this, clearly. Basically, what the paper does at a very high level, again, it groups main memory into sets of rows, and it basically samples the rows. Basically, it uses different fixed caching granularities for different sampled row sets, and basically decides, oh, okay, this caching granularity is performing better at this point in time for this application. So I'm going to use that caching granularity for every other row that you have, that I use in main memory. So the rest of main memory follows the best granularity, basically. So it's a simple idea, basically, that's based on sampling. You dedicate some memory sets to different caching granularities, and you pick the one that's performing the best. And if you do your sampling nicely and well, it turns out this actually provides good performance over here, as you will see in the results. But of course, the cost-benefit analysis needs to be carefully done. How do you actually do the cost-benefit analysis? I'm not going to go into details, but basically you're reducing the access latency, but you're paying a cost. The benefit is reduced access latency, clearly, because you hit in the cache. But the cost is you're moving data and you're actually occupying space in the DRAM cache, right? And the paper has a heuristic to determine this cost-benefit analysis. And again, this is a quantum-based mechanism that does this caching granularity analysis every quantum for different applications, such that it tries to adapt to the application characteristics. For example, if at this point this application benefits from larger caching granularity because it's streaming through a lot of data, then you actually capture that. If at this point this application benefits from this caching granularity because it's doing random access, you capture that. If at any point the application has multiple different access patterns at the same time, unfortunately, this this policy is not able to capture that. And ideally, that's what we should shoot for going into the future, but that increases complexity, right? Ideally, for data that requires smaller caching granularity, you should identify that and use smaller caching granularity over there. And for data that requires large caching granularity, you should use large caching granularity. I like thinking of streaming data versus random access data, but not completely streaming data. You should really have some reuse in your streaming data when you actually do the caching, right? Okay. Let me give you the performance, and then I'll take questions if there are any questions over here. But this figure is a bit crowded, but the last portion over here is everything that I've discussed. Tags in memory, cache the tags in the memory controller, and use this dynamic granularity management policy. And if you do that, you get very close to the performance of a perfect SRAM-based tag store. So basically, we actually close the gap. Instead of having a tag store completely inside SRAM in memory controller, we store it in memory, we manage it nicely, and we get close to the performance of that tag store. And in between, there are some results, but I'm going to skip that because we don't have a lot of time to discuss. You can read this short 4-page paper that discusses this idea. And if you actually apply all of these ideas, you actually do better in terms of energy efficiency compared to a SRAM tag store. Why? Because you're careful in what you're migrating between memories. You have a dynamic migration granularity. You don't migrate very large blocks. You reduce the channel contention. And you also don't have the very large overhead of a very large tag store that's in SRAM. So your energy efficiency actually improves if you have a hybrid if you have a DRAM cache managed using the principles that we discussed earlier. So in that sense, I think this sort of ideas are quite good because they don't lose that much performance, but they improve energy efficiency, and they're much more practical, clearly, compared to huge tag stores inside the memory controllers. So this sort of ideas are actually closer to implementation in hybrid memory systems. Okay, any questions? Okay, I see one hand raised, so please go ahead.
Yeah, just understand the, oh, there's a bit of reverberation.
I can hear you still. If it's not too comfortable, feel free to continue.
Okay. Oh, that's the same problem. Okay, so yeah, just understand I guess, coherence between the three ideas. It's that the first two deal with the problem of storing this massive amount of metadata, and the last one stores with the proper granularity with which to move data. And then, like, I guess all three of them, like, the goal is to then, I guess, to improve the scalability of large caches.
Exactly. And you're absolutely right. The first two are solving a different problem than the last one. And the last one can be independently applicable, as we show in the paper also, actually, to memories, even without the first two.
Okay, I see. And so, like, I guess the first two mostly correlate to the first graph, and then the last one sort of like deals with the last graph, because you're moving like less data than you, or you're moving data more, I guess,
not exactly. I mean, this graph, this performance graph, I think you're mentioning performance graph, right? So, okay, let me give you, I guess what I will say is, this is the state-of-the-art mechanism. You're seeing my pointer, right? Region-based. So this is pure SRAM based tag store. This is a state-of-the-art mechanism that uses tags inside memory, but not in the same row buffer. This is the performance improvement you get if you actually put the tags inside the row buffer, still inside memory. This is the performance improvement you get if you actually cache the tags inside a small SRAM structure in the memory controller. And then on top of that, this is the performance improvement you get if you do the dynamic granularity management. So dynamic granularity management actually spikes performance as well, because it's not wasting your DRAM cache space. And it's also not causing channel contention. Does that make sense? So basically, this is the benefit of the first idea. This is the benefit of the second idea. This is the benefit of the third idea as you keep incrementally adding them.
Okay, that makes sense. Yeah, thank you.
That's true for the energy efficiency graph, by the way. Okay, let me try to move. Okay, yeah, this is the benefit of the first idea in terms of energy efficiency, second idea, and the third idea, incrementally added together. Okay. Okay, if there are no questions, I will continue. I don't see any questions in the room. There are a couple of questions in the YouTube. I see it on my cell phone. Let's see. I don't know when they were asked, but one question is asking, here we're talking about L2 caches, right? I don't know what the context is, but in everything we have talked about in this particular paper and the earlier papers, we're talking about essentially DRAM caches. You can call them L4 or L5 caches, depending on what granularity, or what level, how many levels you have. So I would call them DRAM caches, basically. They're not L2 caches, no. And the other question is, in Intel latest hybrid CPUs, it will be interesting to dedicate fast memory to performance cores and slow ones to efficiency cores. So that's interesting, actually. So we have not talked about heterogeneity in the cores. That's kind of the topic of the next part of the lecture. But certainly, if you have different types of cores, and if that means that the different types of cores are fundamentally are executing applications that need fast memory, then that may make sense actually as a partitioning. But in my opinion, fast cores, applications that need fast cores do not necessarily need fast memories also. These are two different characteristics that may need to be independently managed. For example, when you need fast cores, maybe you need to do a lot of computation and you're very compute bound as opposed to your memory bound. In that case, having fast cores with large caches allocated to them may be a good idea, but maybe you don't need a lot of memory bandwidth in that particular case. So I think it really needs to be investigated, this combination. So far we've been talking about hybrid main memories, but if you add the combination of hybrid cores, heterogeneous cores, and heterogeneous memories, how do you manage them together at the same time? What threads should be allocated heterogeneous cores and what threads should get what fraction of the heterogeneous memories becomes very interesting and becomes also more challenging as well, right? So that's a very good point. But I don't think the answer is as simple as allocate the fast memory to fast cores and allocate the slow memory to slow cores, because the needs of the fast cores in terms of memory may be different than the needs of the slow cores. Okay. So the rest of DRAM caches, there's a lot of literature in this topic, actually, as you can see. There are actually some works that propose purely software-based management and some purely hardware-based management and some hardware-software cooperative management. As you can see, this is a table from one of our papers that was published in Micro 2017, which is a hardware-software cooperative paper. I'll give you the basic ideas very quickly of this paper, but I will not go into a lot of detail, again, because we don't have a lot of time. And if you go into a lot of detail, there are a lot of works over here. But I find this fascinating. You can see that, for example, there are policies that you need to employ when you have a DRAM cache hit and what happens on that case. There are policies that you employ when you have a DRAM cache miss. How do you determine that? There's policies in terms of replacement. Who makes the replacement decision? Does the hardware make it? Does the software make it? Is it cooperative? And large page caching. How do you deal with large pages? So, okay, 4 kilobyte pages, maybe you can manage. What about 1 megabyte? What about 1 gigabyte? Now it becomes harder to move data of those huge pages, right, between memories. And the question is, how do you actually support these? And these different techniques that are mentioned over here have different reds and greens in terms of management. And our work actually is proposed at the time to actually solve the downsides of prior mechanisms. That's why you see all greens over here. But you can see, for example, some characteristics. The replacement decision is hardware managed, it's set associative, it's frequency based, meaning based on the frequency of misses to a particular page, predicted frequency of misses, you decide which pages are hot, which pages are not hot, and basically do the put the hot pages into the fast memory. This doesn't take into account, for example, robot for locality. I believe it can be improved by taking into account robot for locality, memory level parallelism, but it's hard to take into account everything concurrently at the same time. And maybe future works will need to do that going into the future. But let me give you the basic ideas of this hardware-software cooperative management, if you will. So basically, the idea here is use the virtual memory subsystem to actually keep track of what's in the fast memory and what's in the slow memory. This sounds very nice, hopefully, right? Basically, slow memory is the cache. That's the DRAM cache. Track the presence of the pages in the cache using the TLBs and the page tables. This is now beautiful because now you don't need the tag store for DRAM cache, because everything is already in the page tables, right? Your page tables already provide the translation. Whenever you need to do an access, you need to access the page table to get the translation. And that translation can also tell you, oh, the page is currently in the DRAM cache. So access DRAM cache. So you only need 1 bit, if you will. But of course, the downside here is it becomes hardware cooperative management. And when you evict something from the DRAM cache, you need to modify the page table and the TLBs. And this requires a lot of software changes because modifying a page table and modifying a TLB is not easy. So this paper also proposed a lightweight, lazy management protocol for the TLB so that the TLB updates are done lazily by buffering these TLB updates in the memory controller. Again, I'm not going to go into detail. I think it's a cute idea. It's a nice idea. It actually alleviates a lot of the DRAM cache management overheads because you don't need a tag store now. The tag store is inside your page table. But now you need to manage your page table nicely whenever you do some eviction from your DRAM cache. And also, this paper introduced a new bandwidth-aware frequency-based replacement policy that tries to minimize the bandwidth overhead of moving the data between two different memories. I'm not going to talk about that, but you can see the paper. And the overall results look good, actually, compared to other hardware-software cooperative caches. You can see that the performance is significantly higher, regardless of the DRAM cache latency and DRAM cache bandwidth in this particular case. And it's always good to, whenever you actually do these studies, it's always good to have graphs that look like this. Basically, you sweep the cache latency, you sweep the cache bandwidth, you sweep the different parameters so that you can see the sensitivity to different parameters. And the paper analyzed a lot more, but we don't really have time to go over that. So if you're interested, this is actually an interesting work that we did with Intel to show that there are better ways to actually manage DRAM caches using software-hardware cooperation. And Intel was clearly quite interested in this because Intel has had these DRAM caches in their processors earlier than many other systems. These Knights Landing processors, for example, they had I think what they called it multi-core DRAM or something like that. But they basically had a DRAM cache to enable high bandwidth, low latency access to large amounts of data. And they needed to manage this DRAM cache at low overhead. And this is one mechanism that reduces the overhead of that management of the DRAM cache to as little as possible, if you will, in the hardware. Okay. If there are no questions, then I will move to other opportunities with emerging memory technologies. But I will maybe repeat that the work in hybrid memory management needs to continue. And I think going forward, we will see much more model-based and machine learning-based policies that take into account many, many different dimensions. Because as humans, we're not able to take into account many different dimensions at the same time. We put heuristics, but these heuristics usually break down under some cases. They're not optimal. They're certainly not optimal, but in many cases, they're very suboptimal as well. Okay, I don't see any hands, so I will jump into other opportunities. Okay, other opportunities are actually quite exciting also. Too bad we don't have a lot of time, but I will mention several of these. One is you can merge memory and storage. I'm going to cover this a little bit later. You can enable new applications, and people are always interested in finding new applications that can benefit from non-volatile memory. And I think, for example, very fast boot up. Clearly, that's maybe a boring application, but still, booting a computer very fast is interesting with non-volatile memory technologies because it could be extremely fast. Intermittent computing, when you don't have a lot of power in the field, for example, in Internet of Things, when you have a lot of devices that don't have a lot of power or that get powered intermittently, having non-volatile memory coupled with computation is very nice because you can quickly checkpoint your data. Whenever you're losing power, for example, you can quickly checkpoint your data inside your non-volatile memory, and you can judiciously use your computation power because you're very much power limited. Whenever power comes back up, you can basically move the data for DRAM, for example. So non-volatile memory and emerging memory technologies enable this ultra-fast checkpoint and restore potentially. But of course, you need to enable applications that can take advantage of it. More robust system design, potentially you can reduce data loss, especially in power-limited scenarios like we discussed briefly. Maybe these two go hand in hand. But I think robust systems, one of the reasons, if you have volatile memory, you need to actually put your data to persistent memory once in a while so that you don't actually lose data on a power outage, for example, or a failure. And the less frequently you move your data from your volatile memory to persistent memory, the more likely that you will be vulnerable to reducing to data loss or failure, right? Whenever power fails, for example, there might be some data in your DRAM that you were supposed to push updates to your SSD, but you didn't get a chance to because power failure happened. And this is clearly not good if that data is really needed to be updated in your SSD. So a more robust system design can be enabled if your DRAM becomes persistent, clearly, right? Meaning if your main memory becomes persistent. We'll briefly talk about that at the end of this lecture, but I will mainly point you to some papers because we will not have time. But I think this is also very important and interesting. And finally, some topic that I promise we will get back to, processing tightly coupled with memory, becomes even more interesting when you have emerging technologies because they enable new opportunities. Basically, they enable efficient matrix vector multiplication plus search and filtering, as we have discussed in the past. But let me focus on this one first before we move to the merging of memory and storage. So I'm going to cover especially processing tightly coupled with memory quickly and merging of memory and storage, hopefully also quickly. Okay, so recall processing using memory. We discussed processing using memory. You're very familiar with it right now. In DRAM, for example, we can support bulk bitwise operations using analog computation capability of DRAM. By activating multiple rows, we can perform computation. We can do row clone, for example. We can do m-bit, in-memory bulk bitwise operations and or not majority. And you've seen significant benefits using this. Basically, new memory technologies enable the same opportunities. I will show you, we've actually discussed one paper that enables these opportunities. I'll discuss it a little bit more quickly. But any new memory technology has similar characteristics as DRAM, and they basically enable this sort of analog computation by doing n-row activation. But they also can operate on data with minimal movement because DRAM fundamentally is destructive. Whenever you activate a row, you're destroying the row, right? That's not the case in emerging memory technologies. These, well, most of them at least. They're non-volatile, right? Whenever you activate a row, you're not destroying the data in the row. So you can actually operate on data with less movement in this case. So just to jog your memory, we discussed in DRAM, bulk bitwise and or in DRAM computation in general, and in DRAM bulk bitwise execution engines. We discussed SimDRAM, for example, and these are the jog your memory, the lectures that we have covered. Some of them we have pointed to, but we've covered this actually a lot in earlier lectures. Basically, the same operations that m-bit proposes can be done in non-volatile memory as well. This is a paper that talks about the operations. Because we have covered this a lot, I'm not going to talk about this in detail. But the paper essentially says that you can do n-row bitwise operations in non-volatile memory in one step. They also add some more. Basically, they need to modify the sense amplifier to enable this. Again, I'm not going to go over this, but m-bit also requires some modifications clearly to part of DRAM to enable this reliably. But in non-volatile memories, the concept is very similar. By activating multiple rows, you can enable multiple row computation, bulk bitwise computation across those rows. And this paper shows significant benefits, just like m-bit paper also shows. What is new? Let's talk about what is new so that's good, basically. Basically, what we have talked about earlier is very fundamental. It's applicable to multiple row activations, applicable to multiple memory technologies. So we can actually do processing using non-volatile memory as well, using multiple row activation. Let's talk about what gets enabled in these new technologies that is very difficult to do in DRAM, in at least current DRAM structure. And that's going to be this in-memory cross-buy array operations. So basically, the reason these are possible in emerging non-volatile memory technologies is because they have crossbar array structure. You will see an example of this picture soon. And essentially, any of these memory technologies have this array structure, but memristors and RRAM are actually quite investigated, let's say, in literature to support this. People have built actually prototype chips that can do these operations that I'm going to discuss in a little bit. And basically, these crossbar arrays can be used to perform dot product operations. Basically, these are vector dot product operations using analog computation capability. Why? Because you can operate on multiple pieces of data using Kirchhoff's laws, which say that bit line current in a bit line is a sum of products of the word line voltage times the resistance or conductance, 1 over the resistance of all the cells on the bit line. I'm going to show you this pictorially, so you don't need to completely understand at this point, but hopefully this makes some sense. So computation is done in the analog domain inside the crossbar array, basically, which means that you need to have peripheral circuitry for digital to analog and analog to digital conversion of inputs and outputs. Now let's take a look at this pictorially. So this is the crossbar structure. You can see that this is a crossbar. This general structure, two-dimensional structure, is called the crossbar. Let's take a look at 2 word lines over here and 1 bit line. You can see here we have 4 word lines and 4 bit lines, right? It's 4 by 4 array. But if you look at this 2 word lines and 1 bit line, if I apply voltage 1 on one word line and voltage 2 on the other word line, and if I have conductance G1 on this resistor, which is the memory cell, because remember, the memory cell is a resistor. These are resistive memories. So a memory cell stores some resistance. So you can treat that as a resistor. So this memory cell stores some resistance, which means that it has some conductance. G1 is conductance, which is 1 over R1. And then this memory cell has another G2 conductance. Based on Kirchhoff's laws, the bit line current that I get in the output after applying voltage V1 and voltage V2 over here will be voltage V1 times conductance G1 plus voltage V2 times conductance G2 over here. If you're not familiar with conductances, this is G1 is 1 over R1, G2 is 1 over R2. So this is basically no different than Kirchhoff's laws. Kirchhoff's laws means that at a terminal over here, you sum the currents that are coming to that terminal, right? Basically, what is the current over here? The current over here is V1 times G1, V1 divided by resistance over here. Current here, and then you add to it the current over here, which is V2 times G2. And hopefully that makes sense. And now you're doing analog computation. You're basically mixing voltages with currents. And as a result, the current that you get at the end is a representation of the computation that you've done based on the voltages that you have input over here and based on the resistances that were programmed into your memory. So this sounds quite cool, clearly. And you can actually do this in a larger array, as you can see, 4 by 4 array over here. But of course, you need to have digital to analog and analog to digital converters, as we will see in a little bit. But you can also read some of these papers that discuss these issues. And as I said, people have prototyped these in RRAM circuits, and they have reliable operation in RRAM circuits. But let's take a look at this in a little bit more detail. I've given you everything, basically, almost. But this is the 4 by 4 version. You basically, whatever computation you want to do, let's say you want to multiply a vector using a matrix. This is your matrix. You basically represent your values in the matrix using resistances. And you program your resistances into this array of memory, which is the non-volatile memory, as we discussed. And then you basically input your vector in terms of voltages. You need to program those voltages clearly. And you input your vector in terms of voltages. And the output is a multiplication of this vector, this input voltage vector, with the resistance vector that you have stored over here. And the output is really the current, which is the sum of the multiplication of the voltages and the conductance over here. That's I1. I2 is essentially the same equation applied over here. I3 is applied over here. I4 is applied over here. Basically, at the end, in each bit line, you have I1, I2, I3, I4. And those are the dot products of this vector with the vector, the column vectors that are stored in the matrix. So this sounds cool, clearly, right? And then this is the computation that you can map on top of the matrix. You need to store your weights clearly. These are called weights in the matrix. And this basically kind of pictorially demonstrates what's going on. And you have your outputs. Okay, so to really make this work, you need to have a digital to analog converter. And at the end, you need to have sampling and holding logic and an analog to digital converter. You can think of these as big sense amplifiers to make sense of what's happening. And then you may want to have a reduction logic. For example, if your goal is really to sum up the bit line currents, you may need to do a shift and add, for example. But again, that's used to summarize the final output. You may not need that. So you may need to have some other digital logic over here to take advantage of the results coming up. But clearly, to make this work reliably, you need to have a digital to analog converter and an analog to digital converter. And those are actually the most costly components. The array computation is actually not that costly because we're just taking advantage of the analog operational properties of the resistive non-volatile memories. Okay, so all of this is in analog, everything else is in digital. Okay, so what this is really useful for is clearly matrix vector multiplication, but filtering also, convolution, in other words. And convolutions are, as we discussed in the past, are very useful for neural networks today, right? I'm going to give you some examples quickly of this. But basically, in a neural network, in one stage, you have an input feature map. Basically, input feature map are the inputs to that stage. And you basically apply some filtering convolution operation to that input feature map using some kernel, which is this gray filter that's going over this input feature map. Basically, that's the convolution operation. To all of the inputs that are coming, you apply some convolution operation using a kernel filter, which has some weights. And basically, you produce the result. That's the output feature map, output matrix, if you will. And all of the convolutional layers in neural networks look like this. You have an input feature map. You produce an output feature map by convolving the input feature map using a kernel. And you can think that you can store the kernel inside your non-volatile memory and pass through your inputs to do the matrix vector multiplication so that you can get the output feature map, each of the outputs in the output. And that's the idea over here. The kernels get stored inside the main memory, inside non-volatile memory. Inputs get passed as voltages to the word lines. Of course, you need to make sure that your inputs are sent in a nice way because clearly your input feature map is much bigger over here than your kernel. So you need to process your inputs and pipeline them. And then you get the outputs in the bit lines. And then you can basically produce your output feature map. And then you can feed that into some other neural network that does the next stage. And that's the idea over here. So basically, by taking advantage of these non-volatile RRAM resistive memory arrays, you can have one convolutional layer implemented. You can feed the output of that convolutional layer to the next convolutional layer and feed the output of that convolutional layer to the next convolutional layer. Of course, if some layers are not convolutional, you need to implement some logic on the memory device so that you can take advantage. You can basically compute that logic, or you need to move the data somewhere else outside the memory device so that you can do the computation. If you have 3D stacked memories, logic layer is a very good place to actually do the complicated operations in neural networks, for example. Okay, so hopefully this gives you a high-level idea, but this is basically what I said, kind of visualized. So your kernels may be larger than your non-volatile memory. So you need to actually put your kernel to multiple non-volatile memories potentially. Your inputs may be larger than your non-volatile memory. So you need to actually linearize your input as a vector and then pipeline it so that you keep sending your inputs to the kernels. And the result will be outputs that are accumulated at the end over here in the array. And then you can basically put those resulting outputs, basically pipeline them and give them to another non-volatile memory array. So this is your non-volatile memory array over here. Inputs are pipelined, sent as vectors. And clearly this is a three-dimensional input over here, but you need to vectorize them, create vectors, columns from them, and then match the columns to the kernel columns that you create and store as weights inside the resistive memory array. And then you capture the output at the end. And you can store the output in non-volatile memory also, some parts over here clearly as they're not depicted over here necessarily. Okay, so hopefully this is clear. But if you really want to create a non-volatile memory-based processing in memory system, and if you also want to do processing like non-convolutional, non-matrix multiplication operations, you need to add some other operations. So this is the vision of a system that has DRAM and non-volatile memory-based processing in memory. And the non-volatile memory has two different types of arrays. Some of them are dedicated for memory. Some of them are dedicated for processing, let's say. Of course, you can manage them in different ways also. And then if you look at the processing subarrays, hopefully most of the chunk is doing analog computation like we have discussed. But sometimes you need multiplication outside, summation, for example, reduction operations. Sometimes you need nonlinear functions outside that you cannot do in neural networks. And hopefully most of your operations are done in this processing in memory array over here. But again, because neural networks are not just about matrix multiplication, you need some other operations implemented. So that increases the cost of non-volatile memory. But as we discussed in the past, these operations can also be done in the CPU with some data movement. Okay, any questions? And feel free to ask questions, but these are some papers that I would recommend people to look at. These are some early papers on the topic from, well, not the earliest papers, but some papers that actually discuss how to map neural networks to these analog crossbar-based memories. And you can see that some of them are actually published in Nature. People have actually demonstrated some of the earliest devices that can do this in memristors. Today, actually, we have much bigger arrays that can do this computation much more efficiently, let's say. And going forward, who knows, maybe we'll have devices that can actually do this computation. I think one downside today is these arrays are small. Going into the future, hopefully the arrays that can do this computation will become larger and more reliable. As a result, we'll be hopefully able to do more matrix multiplication and larger matrix operations in these arrays. But today, we're limited by the size of the array at this point. As a result, you need to have many, many arrays, and you need to do multiple digital to array, analog and analog to digital conversions between the arrays. And the size of the arrays are usually limited by reliability concerns, like you lose, for example, signal strength, right? When you have analog computation, you are subject to noise. You're subject to different types of disturbance issues because you're doing this analog computation inside the array. And as your array becomes larger and denser, these type of noise effects becomes more and more significant. As a result, currently the array sizes are limited. But going forward, hopefully, people will be able to solve this, and we can actually take advantage of these larger arrays to do computation. Okay, I don't see any hands, but feel free. So one thing that we did not cover, this is an example of a systolic array, actually. So what I have shown you over here is you have a systolic array. You basically have your kernel inside your weights in the kernel put, and then you basically stream your inputs and you get the outputs. And you basically orchestrate the streaming of your inputs so that you get the correct outputs matching in the end by enabling the analog array to do computation for you. And this is a form of systolic array, and systolic arrays are not necessarily coupled to RRAM. They're actually a much bigger concept. Basically, you enable these cells, let's say two-dimensional or one-dimensional cells, and you basically orchestrate the data movement into the cell such that the different pieces of data meet each other in the cell at the right point in time, such that the right computation happens, and then the output gets streamed out of the cells. And that's essentially what we have discussed. If you want to learn more about systolic arrays, I would recommend you take a look at the digital design and computer architecture lecture that we covered in previous incarnations. If you have time this year, we will cover it in computer architecture as well, but we may not be able to cover it. If you've already seen it in digital design and computer architecture, you should already be familiar with what I have discussed very well. Okay, any questions? Okay, so if there are no questions, let me go over this merging of memory and storage, and then we will take a break before we go into lecture 17B. So this is actually quite exciting also. If you think about how we design systems today, we have memory and storage that are quite dichotomous from each other. We have memory, we program it using loads and stores. We have storage, we do completely different things, file, IO operations, right? And this is because these different memories have very different characteristics. So, okay, sorry about this. Something is, okay. So storage memory, the storage devices are non-volatile, slow, and block addressable today. Whereas DRAM is volatile, fast, and byte addressable. As a result, and it's extremely fast compared to the storage technologies that we have today, even SSDs. And as a result, these two have evolved differently. And we have two different interfaces to them. Non-volatile memory enables another opportunity. It kind of sits in between, as you can see. It's fast, byte addressable, and non-volatile. So it doesn't have the downsides of hard disks. And it doesn't have the downside of DRAM. Well, it's slower than DRAM, yes, but it doesn't have the downside of volatility. So it combines the non-volatility with fast operation and byte addressability. As a result, it enables the opportunity to get rid of both DRAM and hard disks in the system, let's say. This is a unique opportunity, let's say. And it also enables an opportunity to rethink the interfaces that we have in our memory, in essentially our memory and storage models. So basically, this is what I just discussed. We have a traditional two-level storage model. Volatile data is stored in memory using a load-store interface, and we do address translation, for example. We have heavy hardware acceleration for this because main memory is very fast. Persistent data is stored in storage, and we use a file system interface that's relatively slow, that takes microseconds and microseconds, because storage takes microseconds, right? Let's say. And we have a file system interface. Now we are kind of happy with this picture. Now, people who want high performance are not happy with this picture because this operating system and file system calls that you need to do to actually manipulate files and buffer files so that they're buffered in main memory and then you write them back to storage, etc., is causing a lot of trouble, basically. It's a lot of overhead in the system. So if you want high performance, this is not good. But this becomes really, really intolerable if you replace the storage device, SSD or hard disk drive, with an almost DRAM-like fast memory, phase change memory, but that's non-volatile. So basically, the overheads that you have in the operating system and file system to do the file system management, to locate, translate, and buffer data in DRAM, because usually what you do is you do memory mapping and you memory map a file, which really needs to open the file. It takes some amount of time, and you memory map it into the main memory, and then you manipulate the file in main memory, and then you write it back. And while the file is inside the main memory and you've written it back, it's vulnerable because it's not in persistent storage, as we discussed. So it caused a lot of overheads and trouble and headaches to a system designer to operate this reliably. They also become performance energy bottlenecks, even more if this is fast enough. So if this is really fast, now this is a nanosecond level memory. Managing it at the microsecond level operating system and file system function calls makes no sense. Basically, you're using a very fast memory and you're basically slowing it down. So I think non-volatile memories require us to rethink how we design our entire data management systems. So if you look at this load store based systems, it's heavily accelerated because its main memory is extremely fast, right? But it is not non-volatile. So the question becomes, can we unify memory and storage management in a single unit to eliminate all of that wasted work to locate, transfer, and translate data between storage and main memory? And we can improve energy and performance, as I will show you. This also hopefully simplifies programming model as well, because now we can actually use only loads and stores in our systems. And I think this is going to be fascinating and fun. So basically, the idea is to have a persistent memory manager, which takes loads and stores with some potential hints and characteristics. It provides feedback back, and it manages itself. So persistent and non-volatile memory are all together in this persistent memory, which can be phase change memory potentially, right? Which can be heterogeneous also, as we will see. But basically, it looks like this. We have a load store management, and this provides an opportunity to manipulate persistent data directly. Now you can have persistent data structures. So if you look at your programming languages today, your data structures are all volatile, right? If you want to make them persistent, you need to write them to a file. Now we have a different way of thinking. Let's make our data structures persistent as well. If a data structure needs to be persistent, declare that as persistent and manipulate it with loads and stores. Why are you dealing with file system calls? Don't deal with file system calls. Just do a load, you get the data directly from a persistent data structure, persistent file. Just do a store, you update a location of file. Of course, you need to do this correctly, meaning security, etc., needs to be handled well. But the performance of this could be extremely high if you can handle the security, etc., well. So we'll talk about that security, etc. aspects. But the idea looks like this, basically. You may have a persistent memory-based programming model. You may have persistent objects. So file opening looks like this now, right now. Your file is an array of characters, potentially. And then you can update your file nicely, and the value is persistently updated in main memory using loads and stores. Programming becomes a bit easier this way. You just need to say what is persistent and what is not persistent, potentially. That's going to be important, I think, because distinguishing persistent and non-persistent data is important for performance as well. And then you have a persistent memory manager underneath. It gets these loads and stores, also hints from software, OS, and runtime and the application, saying that this data needs to be persistent. These are the security requirements, etc. These are the people who can have access to it, etc., just like files. And then the persistent memory manager does the data layout, persistent management, metadata management, and security. And underlying devices can be anything. It could be DRAM, it could be flash, it could be non-volatile memory, it could be hard disk drives. And basically, the persistent memory manager takes advantage of the speed of the fastest devices over here and capacity of the largest device over here, such that it can intelligently manage data underneath. So I think this is an interesting direction, certainly, as we're going to see with the results also. But this persistent memory manager uses access and hint information to allocate, locate, and migrate and access data in the heterogeneous array of devices. Now let's take a look at what it needs to do. So it exposes a load store interface to access persistent data. Applications can directly access persistent memory this way. No conversion, translation, location overhead for persistent data, because all of that management, well, certainly whenever you update persistent memory directly, that management needs to be done a little bit by persistent memory to ensure security. But this is high performance because you don't need to go through file system calls. Okay, it manages data placement, location, persistence, and security to get the burst of multiple forms of storage. And it manages metadata storage and retrieval. Basically, what data should be stored where. Clearly, this is, again, looks like a tag store, right? Metadata, you need to associate the data structures with where they are stored currently, what are their characteristics. And this needs to be managed well. According to this paper that we did some number of years ago, if you don't manage metadata well, overheads can be very large. So you need to be very careful in terms of managing the metadata. It also exposes hooks and interface for system software as well as the applications such that it can enable better data management and placement decisions. Let's take a look at an example over here. So basically, a persistent memory exposes a large persistent address space, but it may use many different devices to satisfy the goals of different data. So for example, you can have fast, low capacity volatile DRAM to slow, high capacity non-volatile hard disk drive or flash and other NVM devices in between. And performance and energy can benefit from good placement of data among these devices. As we discussed, you can utilize the strengths of each device, avoiding their weaknesses if possible, but you're using loads and stores to do the management and some hints. Let's take a look at some application level characteristics. Consider two important application characteristics, locality and persistence. And you can, I think, classify any data in terms of two extremes in locality and persistence continuums, let's say. Some data has less locality, some data has more locality, some data is temporary, and some data is persistent. And there are many, many examples over here, but I'll give you some examples. For example, columns in a column store database that are frequently scanned, that are infrequently scanned. You can place these on flash because you're doing streaming accesses, scan accesses in a large column in a column store. So you have low locality basically, but you need persistence, right? So this makes sense to place in flash because you don't want to waste, let's say, money and cost on more expensive devices over here. And you're streaming because, as we discussed, streaming data can be handled very nicely by buffering in different parts of the memory hierarchy. You don't need expensive memory devices. In fact, all you're doing, if all you're doing is streaming through memory, through data, like just watching a video, no random access, just streaming, nothing else. Why not store everything inside a tape, for example? That's really slow, but do enough buffering and give enough streaming bandwidth, because streaming is really a bandwidth problem. And your bandwidth can be maximized by using row buffers, for example, buffering. And then the rest is basically ensuring that your streaming bandwidth is enough such that people do not notice the latency problems, right? Your latency may be very high, but if your streaming bandwidth is high enough, you can hide that latency, right? That's why this sort of data makes sense to place in low-cost memories that enable persistence. But there could be other data that are exactly opposite. For example, you have a content delivery network, and you have an index that is frequently updated and reformed so that you can decide where to go, for example, where to look up. You can place this in DRAM because it doesn't need to be persistent. You're just updating your index quickly, and it's also write intensive, as you can see. You can place it on DRAM, you have more locality, and it's temporary. So at the application level, at the system level, you have a lot of information about the characteristics of your different data, basically. Why not communicate this through a persistent memory manager interface to your system, such that your persistent memory manager can do the right decision for allocation? And that's the idea over here. So I'm going to give you an example of results if you do this management nicely for a number of applications. You can read the paper for more detail, but we're going to evaluate three different systems. One is hard disk drives. This is not the state of the art clearly today because we have solid state drives, but this is a traditional system with volatile DRAM memory and persistent hard disk drives. And clearly, whenever you access persistent data, you have the overheads of operating system and file system code and buffering. Non-volatile memory baseline replaces hard disk drive with phase change memory, something extremely fast, basically. But it still has the operating system and file system overheads of the two-level storage model. Basically, we're going to show how bad these overheads are to motivate that we don't want to manage the non-volatile memory baseline with operating system, file system calls to manipulate persistent data. And then the persistent memory is what we are proposing. It uses non-volatile memory, only non-volatile memory, not even DRAM. Basically, in this case, not even hybrid memory. We ensure full system persistence over here. All data is accessed using loads and stores. It doesn't waste time on system calls. So this is going to be the most performing baseline, but it's not even going to apply the hybrid memory principles, because while we were doing this research, we did not think hybrid memory was actually good enough to take advantage of it. But I think right now you can apply the hybrid memory principles to it and get even higher performance on top of it. Here, data is manipulated directly on the non-volatile memory device. We don't even have DRAM in this system. So, okay, to recap, here we have hard disk drive and DRAM. Here we remove the hard disk drive, replace it with phase change memory. Here we remove the DRAM and also replace the operating system and file system management with direct load store access. As a result, going from hard disk drive and replacing hard disk drive with phase change memory, we get a lot of benefits. Going from non-volatile memory getting rid of DRAM and replacing the management with 2 load stores buys us benefits, even though we got rid of the fast memory in the system. So here we have phase change memory. Here we have same phase change memory. We got rid of DRAM that's present here. We got rid of DRAM in this particular case, but we got rid of the bad management, slow management of phase change memory. We just use loads and stores. And as a result, we get 5x more performance improvements. So this shows you that clearly the bottleneck going from here to here has shifted to system calls. Here you're waiting for the device most of the time. So the device is the bottleneck. You get 24x performance improvement by getting rid of device bottleneck. Now your system calls become the bottleneck. You get rid of that and you get 5x more performance improvement, even though you get rid of the faster memory in the system, which is DRAM. So this is very promising, as you can see. If you add DRAM into the system and do better hybrid memory management, I believe you get another 2x at least, maybe even more, depending on how much DRAM you add into the system, of course. Now you can say that this hard disk system is a little bit old, and yes, I agree. We should have done this. We should have also shown the SSD system over here. SSD would bring us to, let's say, 2x, 2.5x performance improvement over here, such that this 24x doesn't look as dramatic, if you will. So SSD would be somewhere over here, according to our results. Okay, energy efficiency is similar, actually. You can see that the energy reduced by 16x, going from hard disk to non-volatile memory, and getting rid of the inefficiencies in non-volatile memory management, you get another 5x. Again, still by improving the fast memory in the system, fast and reasonably energy efficient memory in the system. So you can see that the benefits of unifying the memory management and getting rid of the system call based memory management and turning that into load store based single level memory management, single level interface can have a lot of benefits. If you're interested, this is the paper that I gave you results from. This paper has a lot of other results. And I think, there has been a lot of other works that some of them I will quickly mention since we don't have a lot of time. I would recommend you take a look at it. But I think going forward, this emerging memory technologies have significant system level implications like this. But we do need to rethink the system to enable such ideas. Okay, any questions? Yes, please go ahead. I see a hand raised.
You said that if you did like persistent memory plus a hybrid system, it would have had probably another 2x performance increase.
Yes.
How did it affect the energy efficiency? Since you add in potentially DRAM again, would it actually be less energy efficient then?
Yeah, that's a good question. I think, okay, so it really depends on how much DRAM you add. If you add huge amounts of DRAM, yes, it could reduce your energy efficiency. But in our experience, as well as the experience of some others, the IBM paper, for example, that I mentioned in the last Emerging Memory Technologies lecture, if you have a small amount of DRAM, it improves your energy efficiency a lot because it enables you to buffer data inside the DRAM that would otherwise you have to access in non-volatile memory. And non-volatile memory, like phase change memory, for example, fundamentally, each read is much higher energy, 2x higher energy. Each write is, let's say, I think if I gave you the results from last time, 43x higher energy. So using DRAM as a buffer actually it makes it more energy efficient. But of course, if you add huge amounts of DRAM, the energy efficiency gains you get by reducing accesses to non-volatile memory starts being shadowed by the energy inefficiency of DRAM due to refresh, for example, as well as due to leakage. So you need to add the right amount of DRAM into the system. Make sense? Okay, cool. That was a very good question, basically. Okay, great. I'm running a little bit later, but feel free to ask questions still. The remaining parts of this Emerging Memory Technologies lecture, I'm going to go through quickly, but hopefully this gives you an idea that combined memory and storage using non-volatile memory technologies can be quite effective and can enable us to rethink the systems. In fact, if you think about it, our systems were not two level. Our systems in early 1950s, 60s were actually one level. When people were designing systems, there was no distinction between memory and storage. There was one level stores. Because people were using really slow memories to begin with, let's say. They were used as both memory and storage. And there was no distinction between volatile and non-volatile. Over time, new memory technologies came about. For example, DRAM came about in 1965. Hard disks clearly came about sometime around and after. But basically, they became better and they became diverging from each other. DRAM became extremely fast and hard disks became very high capacity but slow. And as a result, people felt the need that we actually need a two-level model because it doesn't make sense to manage these two completely different devices in the same way. So as a result, two-level model formed. We had volatile data stored in main memory. We had non-volatile persistent data stored in hard disks. And that model has been present with us for a long time. People actually tried to eliminate that model. There was this nice project by IBM, AS400, for example. There's actually a very nice book about it, Inside the AS400. I would recommend you take a look at it if you're interested. It's called Inside the AS400. IBM engineers basically said, okay, these two-level model is not very good, basically. Let's actually have a single-level store so that we don't have the inefficiencies of this two-level model. But unfortunately, their devices were not fast enough. As a result, it didn't materialize. But today, I think we're at a very unique point. We have these devices, like phase-change memory devices, that are fast enough, that are almost as fast as DRAM. They're much higher capacity than DRAM. Why not revisit the idea of using only a single-level memory and storage system, as opposed to distinguishing between files and as well as main memory that's managed using loads and stores. And again, this may be harder to adopt in software, but there may be virtualization techniques that can enable conversion of file systems to loads and stores going into the future. Okay, I think this brings us to maybe potentially we need a unified interface to access all data. If you think about it, today we have very different ways of addressing data. Main memory is accessed in a different way than storage. Network is accessed in a different way than storage. I don't know, some other machine is accessed in a different way than local storage. So local memory is different from remote memory. Local storage is different from remote storage, etc. Why not unify all of that? Why not unify a single way and have a very efficient manager that can actually manage where the data resides? Internet, for example, data resides in some other computer, is managed and addressed and managed in a completely different way, right? But why? Why not have an address space that's large enough to cover every data in the world? Of course, this is maybe pushing it a bit, right? Maybe you need to have different namespaces for internet, but I think it's good to question that also going into the future, as we're going to have very fast networks potentially, as well as very fast storage devices like we have been discussing. So I think emerging technologies can enable this sort of rethinking of the system. Of course, this rethinking of the system comes with some software challenges. And that's something that we need to think about going into the future. Okay. And the good news is I think this is happening. I'm going to flash these, and processing inside the non-volatile memory is also going to be happening. It's already happening in DRAM, but I think it's going to be happening in non-volatile memory. So having processing in both DRAM and non-volatile memory is going to be very interesting going into the future. This also enables another opportunity. Where should you process the data, right? Non-volatile memory, DRAM, what kind of data can be processed better in DRAM and non-volatile memory? These have different characteristics, different devices have different computation capabilities. So I think the future is going to be very, very interesting as these emerging memory technologies become more and more prevalent and more powerful in terms of both computation as well as memory and storage. Okay, there's one topic that I'm not going to cover, unfortunately, because I do want to get to the next topic. And this topic is, how do you ensure consistency of system and data if all of your memory is persistent? And basically, this is really the crash consistency problem. There are two extremes over here. And for example, basically, we discussed this before, basically. You have some updates that you're doing to your data structures, and your system crashes in the middle. And you may not have done all the updates. And if you restart the system, your system is not in a consistent state at this point because your data structure is manipulated a little bit, but you don't know where the manipulation stopped, right? So who handles this basically? Basically, clearly, there's some transactional updates that you need to do your data structure. You cannot update everything in a fine grain. For example, when you're updating a linked list, clearly we lock the linked list today so that some other update doesn't interfere with it. Persistence has similar characteristics, meaning if you're updating a linked list and if your system crashes in the middle of that update, you may not be able to have a consistent state again because you don't know where you stopped, right? So there are two extremes to this problem. If the system crashes in the middle of an update to a persistent data, and if your update is not consistent, one school of thought, one extreme school of thought says that system should handle it. Basically, regardless of whatever happened, system should give the idea of transparent execution to the programmer. Programmers should not have to deal with rewriting their programs or changing their legacy programs such that they work correctly in the entire persistent memory system. This is a bit hard to do because system needs to provide a lot of support. The exact opposite of this extreme, this opposite school of thought is don't provide any system support, let the programmer handle it. And this also turns out to be very difficult. Programmer at least needs to have some sort of transaction mechanisms, locking mechanisms to ensure that persistent data that gets updated in bulk. And they need to have actually mechanisms that these persistent data doesn't, they need to be able to update the mechanisms consistently, let's say. So usually this is a difficult problem, and these extremes are very interesting to examine, but I think the solution somewhere in the middle is the right option. So there are many alternatives in between, basically. Now, let me give you a quick example over here. I said I'm not going to talk about it in detail, but basically you add a node with a linked list. You need to link to the next, and you need to change the link to the previous. But what happens, and this is persistent update, it's a persistent data structure. What happens if your system crashes in the middle and you have no idea where you stopped? Because if you're doing this update today in a single threaded program, you don't protect the data right in any way. And you don't expect the system to crash also, right? So basically, you may actually start with a wrong data when you restart the system. So you may have an inconsistent memory state when you restart the system. Okay, so basically current solutions require this sort of atomic updates. Whenever you insert a node, you do atomic updates. And the goal is to to do atomic updates into the persistent storage device. Unfortunately, you need to rewrite your code if you want to do this. Especially legacy applications may not work. You need to do something with legacy applications. And you need to clearly partition between volatile and non-volatile data. And it turns out it's not an easy problem. There's a lot of burden on the programmer. So let's take a look. If you want to update a node in a persistent hash table, for example, this is what your non-persistent hash table code update looks like, even with some pruning of the code. And you need to basically make your hash table persistent. So your declarations of the hash table, etc., need to be persistent. And you need a new implementation of your hash table access. Your third-party code that you may use for the linked list, for example, can be inconsistent. You need to rewrite it. And operations like this may be prohibited. This assignment, for example, you need to check whether this assignment is consistent, right? And that may be prohibited. As a result, there's a lot of burden on the programmers today. So our approach in one of the works was completely software transparent consistency in persistent memory systems. And the idea is to have the system periodically checkpoint the state and recover to previous checkpoint on a crash. And I'm not going to go into the details of this, but this is one way of doing it, basically. Periodically checkpoint consistent states and recover to previous checkpoints. Of course, if you do this nicely, you can always start from a consistent state because you know what the consistent states are when you checkpoint. You don't checkpoint inconsistent states. That's the idea. Okay, and this proposes a new hardware-based checkpointing mechanism. And it checkpoints at multiple granularities. I'm not going to go into details. And it overlaps checkpoint and execution to reduce checkpointing latency. Because if you do this, if you execute and then checkpoint for a while, and then execute and then checkpoint for a while, that's not a good idea. Because checkpointing is in your critical path. You really need to overlap checkpoint and execution. And this work also adapts to DRAM and NVM characteristics. And I would encourage you to look at the paper because I don't have a time to really go over this. Because DRAM is very good at writes, for example, NVM is really bad at writes. So the writes are handled in bulk in DRAM in this particular case, and then they're written back to NVM in a streaming manner when necessary. So in the end, it performs within 5% of an idealized DRAM that doesn't have any consistency cost, that doesn't have these cache consistency overheads. Okay, I think I will skip this. I've already given you the idea, basically. Checkpointing and running needs to be overlapped, but this requires a lot of system support. You need to maintain multiple copies of data, of the same data, so that you don't overwrite the old data that may need to be checkpointed. In this particular case, you need to overlap or maintain 3 copies of data. And this is the idea, basically. This is one work that proposes extreme, if you will. There are a lot of other works that built on this work later to try to make it more practical, let's say. Okay, but basically, I gave you another challenge. Programming ease to exploit this persistence is not easy. And also, what data structures should a programmer declare as persistent? What data structure should not be persistent is also a problem. And there are works that actually provide tools and libraries to the programmers to enable them to help them basically declare the data structures as persistent or not persistent. And this is, again, not an easy problem. And there are also other consistency issues that I really don't have time to talk about, but you can appreciate them if you read the papers. What we did not talk about is security and data privacy issues, but persistent memory actually leads to endurance problems. They can lead to rarity attacks. Hybrid memories can lead to performance attacks potentially. And data that is not erased after power off can lead to privacy breaches, right? Because you may have some old copy of data that's inside your device, that's inside the persistent memory. And that's basically exposed out there, right? And people can be exposed to these. And these are some topics that are being researched in non-volatile memory, persistent memory, but we don't have time to cover them as well. Okay, so let me conclude. Basically, I think emerging technologies are happening. Regardless of challenges, again, through hardware, software, co-design, we can enable these technologies. And again, if people are naysayers, let's say, if people are doubtful, flash memory was an emerging technology for at least 2 decades. People were actually quite doubtful about flash memory, whether it will make it, whether it will be useful for anything. When it was first brought up in the 1980s, for example, people said, this is not going to be useful. Applications will never take advantage of it, etc. But here we go today, right? Almost all our lives depend on flash memory today. We cannot carry a device that doesn't have flash memory in our pockets. And even our computers are almost hard diskless, let's say, right? Most of our computers, let's say, especially mobile computers, right? So flash memory was an emerging technology 30, 40 years ago, or even 20 years ago, let's say, but it has emerged and it's a real technology that was emerging. And I believe emerging memory technologies that we discussed are emerging technologies and they will emerge also, and they are general purpose. So that's the interesting part, I think. There's some emerging technologies that are being discussed right now are not fully general purpose. I'll pick on quantum computing, for example. Quantum computing is very interesting and cool, no question about that. But quantum computing is, we don't know how to make it general purpose today, right? If you want to make it general purpose, you have to apply general purpose principles to it, like everything we discuss in architecture. But for some things, quantum computing is extremely good, like special purpose, right? So I think we should be talking about quantum computing accelerators as opposed to quantum computing devices, because it's not clear if we can ever have a quantum computing device that can do everything that we want to do. There was this interesting discussion at some point, I think, whether we will have a cell phone with a quantum computer in it. And I think some quite reasonable quantum physicists said that that's not going to be happening anytime soon, because quantum computing is good at some computations, like factoring, for example. But we don't really know how to do general purpose computations with quantum computing today. But that's not true for every emerging memory technology. So if you look at non-volatile memory, phase change memory, for example, it's quite general purpose, right? It can be used for anything, as we have seen. Some of the computation that you do inside there is actually also quite general purpose, like we have discussed with Ambit. Some of it is very special purpose, like matrix vector multiplication. Clearly, not everything we do in the world is matrix vector multiplication. So I think it's good to have a good perspective of emerging memory technologies and what they can enable and what they cannot enable. And I think even though some of the emerging technologies are quite interesting, that doesn't mean that they can replace everything we do. And hopefully that's clear, even in the case of emerging memory technologies that we have examined, right? We've said that it's an emerging memory technology, it's general purpose, but even then it cannot replace everything that we're doing today, for example, DRAM, right? But it can enable general purpose applications, that's a good part. But there's still many research and design opportunities. I will briefly go over them. I think I've given everything actually so far, but enabling completely persistent memory is interesting, what we have discussed in most recently. Computation using and in non-volatile memory-based memories. Hybrid memory systems, there's a lot to do over there. Security and privacy issues, reliability and endurance-related problems. This is something we did not talk about as much, but issues like RowHammer, for example, and write disturbance get exacerbated in these technologies, especially when you scale down to very small technology nodes. And virtual memory systems for non-volatile memory. How do we design the virtual memory system for these huge amounts of memories so that we don't have the overheads? And we have a work called virtual block interface. That's what this means. If you're interested, you can take a look at that work that was presented in an earlier incarnation of this lecture. But I think that brings me to the end. I'm happy to take any questions. Otherwise, we'll take a break. Yes, please.
Yeah, on this problem of what certain texts are good for what, for the crossbar array, because it operates based on analog principles for computation, would you say that even in the best case scenario, if it were to scale, it would still not be used for the highest performance systems? Because if you think about it, like if it got longer, right, for like a larger array, you'd have greater capacitance effects, and so it'd probably be slower than if you just had a bunch of transistors.
Yeah.
So would you say like the ultimate use case for this would be super power efficiency and like edge devices?
Yeah, that's an excellent question, I think. Okay, it's hard to say exactly something, but with the current, I think with the current state of analog computation and resistive memories, I would say, yes, that is the case. I think the current state, as far as we know, what we can do in the current state of analog operations, matrix vector multiplication in these memories, power efficiency is the biggest advantage, but scalability to very large matrix operations is still a problem. So I believe I would answer your question, yes, in the current state, but in the future, I think that may change, right? We may figure out how to pipeline and connect these devices to each other such that we can achieve scalability with smaller arrays. We may not need very, very large arrays potentially, right? And that may actually provide much more energy efficiency such that we can actually have many, many more arrays together doing matrix multiplication, right? Compared to existing digital devices. So I'm not, I think the jury is still out on that one, but that's a very good question.
Yeah, that makes sense, I think. So like, I guess per unit of a computation, the digital would be faster. But the thing is, you might be able to cram in more units of computation just because of how much more efficient this resistive method is.
Exactly. Because performance is not just sheer computation capability, but it's really performance per watt, right? You can always get more performance for a given number of watts if your performance per watt is extremely high. Okay. Is there another question? I see a hand. Yes, please go ahead.
Hear me? All right.
Yeah.
Regarding the consistency issue with the persistent memory, that just sounds a lot like what the issue that you already have with hard disks and SSDs today, where you start to introduce the file system that is then basically just a large data structure that's on your disk.
Yes,
so
absolutely.
How does this differ from these approaches?
Yeah. Certainly, yes. The issue exists in hard disk SSDs. It's also called the same storage consistency or cache consistency problem. Basically, the issue becomes much more exacerbated if you have load store-based accesses to memory. Basically, let's say you can do a store to any persistent data structure. Now you don't have any control, right? And you need to manage this consistency in a fast way because that store is supposed to be fast. Your non-volatile memory is supposed to be fast. So yes, at a fundamental level, the issue is exactly the same. What has become different is the speed at which we can make these updates and how many updates we can make in a given number of, let's say, nanoseconds, and the probability of crashes that can be happening or failures that can be happening. So, and then how fast we should be able to recover from this crash consistency issues, right? How fast we should be able to fix up the data, for example. With non-volatile memories, I think everything needs to be much faster. And also, I think traditionally, it has been the system plus the programmer managing this issue, right? You have file systems managing this issue, but the programmer needs to obey some, let's say, obey some file system interfaces to ensure that everything is consistent. But with load store-based programming of persistent data, we need to have new interfaces to ensure that consistency, right? If it's just loads and stores, then it's not going to work probably.
Essentially, you don't want to have to make a detour through a file system, but just interface directly with the hardware.
Exactly, yes. Because that file system detour is extremely slow, basically, microseconds level. Okay, I think let's take a break right now. Very good questions. I think I'm going to take a break for 11 minutes this time. Let's be back at 3:15, and then we'll continue. We'll start the next part of the lecture. I'll see you soon. Okay, I think we can get started. Can people still hear me?
We hear you,
That
but we
works.
don't see you yet.
Oh, okay. Yeah, I forgot that. Okay, I think you can see me now also, right?
Yeah.
Okay, excellent. Okay. Okay, I think we're going to continue heterogeneity a bit, but we're going to introduce parallelism also, as if we have not introduced it. But at this point, we're going to transition into some more, let's say, computation type of lectures in this class. As you have seen so far, you focus a lot on memory, even though we have touched on computation clearly. You cannot decouple computation from memory, right? But we have looked a lot into the memory systems and how memory system design can enable different types of computation and how it can serve better, how it can be a more central point so it can serve better the applications and the workloads and the systems that we're designing. Right now, we're going to switch a little bit gears into the computation parts, and we're going to talk more about multi-core designs, multiprocessors, etc. And that's why this lecture is titled Parallelism and Heterogeneity. And we have also been talking about accelerators, and clearly using accelerators as a form of heterogeneity today, right? We have a lot of heterogeneous accelerators in our systems, and they also enable parallelism. Enabling a lot of parallelism using those accelerators to maximize performance and efficiency is actually something that's really interesting, that's already happening right now. And on top of this, we're having increasing heterogeneity on the memory subsystem as well. Okay, I think before I go into it, a few of you have already asked me, but I think I'll remind people that we have a lot of research opportunities on these topics. So if you're interested in any of these topics or any topic in computer architecture that's related to computer architecture, hardware, software interaction, and related areas, we have many projects and a great environment to perform top-notch research. And hopefully you've seen some of that in last week's lectures. Unfortunately, we weren't able to cover all papers that I intended to cover in last week's lectures, but we're going to have another session, hopefully later in the semester, where we will cover some more works that you may be interested in. For example, we were not able to cover the random number generation using quadruple row activation in real systems today, which is, I think, fascinating, but we didn't have time, but we will cover that in the coming weeks. But if you're interested in doing research on any of these topics, or if you have any ideas in architecture, feel free to email me and other TAs in the course. Whenever you email me, please CC others as well so that they can help me manage my email load, let's say. And if you're not taking the course, for example, if you're not at ETH already, you should apply online. We have an online application system. But if you're already at ETH and if you want to do bachelor's thesis, master's thesis, or even a PhD or postdoc on the topic, depending on your level, or even just a semester project, then you can feel free to directly email us. You don't have to apply at that point. And we have clearly many research projects on topics that we have covered. These are some examples. And you already know that we're interested in building fundamentally better architectures and systems. And these are some current directions, but that doesn't mean that. And also, if you look online, you may see some research projects, but they're all outdated, unfortunately. In cutting edge research, unfortunately, it's not easy to update everything you're doing and put everything online. It's usually publications lag the actual research. And that's true for the project proposals, for example, that we put online. If you're interested in architecture and if you don't find a project proposal, don't be worried. We are interested in architecture in general. And if the projects that are described up there don't match your interest, that doesn't matter, basically. So you should still contact us. And as you know, we're interested in doing research that spans the hierarchy, algorithms to devices. So hopefully, if that excites you, please reach out to us. And these are some research topics that we covered. And if you actually will be part of the group, then you will be part of a lot of bright students and bright people who are working on top-notch research in the group. And you've seen some of them in the lectures so far. Many of them are your TAs as well. Okay, and these are more ways of getting to learn about the group. And for those of you who may be interested in a PhD at some point, a PhD takes a long time, clearly. A postdoc takes even longer after the PhD because you add some more time. But if you're interested in doing top-notch research, I think doing a PhD is the only way, in my perspective, to do that sort of research. And these are the PhD students and postdocs that are alumni of our group And you can see that they've achieved a lot. And right now they're doing even more, in my opinion, after they got prepared to do even more. And you can find information about them online also. And if you're interested in working with us, I would definitely recommend watching this lecture or mentoring talk that I delivered to students who are interested in research in general, because that's covered a lot of principles. And I will actually ask you to do it when you're interested, when you express your interest to work with us, because I think this is important. And also, if you're interested on our thoughts on computing features, this is a nice interview that I did a couple of years ago, and I think a lot of things that I mentioned over there are still true, frankly. Okay, so that was a quick overview. I think it's good to mention this at this point because people are interested in doing projects. One thing that I didn't mention over here is if you haven't taken our seminar course, I would recommend taking our computer architecture seminar course as well. That's where you get to present and see a lot of cutting edge research and also get experience in communicating the research and presenting it and critically analyzing it, all of which are really important skills for actually doing research. How do you critically analyze and present research is actually important. Communication and research is actually extremely important because you may actually do great research, but if you don't know how to communicate it properly to a scientific audience and to a general audience, then unfortunately your research may not have the impact that it is supposed to have or it should have if properly communicated, right? So communication is actually an important part of a PhD and also projects in our group as well. Okay, any questions on this? You can feel free to ask questions, of course, anytime during the course of this lecture, but I wanted to mention this more properly since we're getting closer to the end of the lectures too. Okay, with that, let's jump into parallelism and heterogeneity. And let me hide this floating meeting controls. So what we're going to cover today and tomorrow are issues in parallelism and heterogeneous multi-core systems and bottleneck acceleration. It's probably unlikely that we're going to start multiprocessors tomorrow, although we will talk about multiprocessors, not except in a heterogeneous sense, let's say, in this case. And these are some readings that we're going to cover. And if you're interested, you can take a look at them. I'm going to mention them. But let me talk about heterogeneity. We've seen a lot of examples of heterogeneity, actually, but let me give you a quick, let's say, perspective on design heterogeneity. So heterogeneity, asymmetry also means heterogeneity, and it leads to specialization, basically. As I said, they have the same meaning, and you can contrast these with homogeneity and symmetry. And heterogeneity is a very general system design concept in general, and also a life concept. We will discuss this, but everything in life is heterogeneous. There's variation in everything, basically. So, and the basic idea, if you have to describe this basic idea of heterogeneity, it's this. Instead of having multiple instances of a resource to be the same, in other words, heterogeneous or symmetric, design some of the instances to be different. In other words, heterogeneous or asymmetric. That's the idea. And in some cases, this is heterogeneous design, of course, right? In some cases, it may not be even under your control, right? Resources may be different by nature, right? And this is really the variation, manufacturing variation that we discussed, right? So there are multiple reasons for heterogeneity. One is you get heterogeneity because of the way nature is. Nature is heterogeneous, and as a result, manufacturing processes are heterogeneous. So you get heterogeneous refresh rates, for example. You get heterogeneous frequencies. You get variation in device latencies and across devices and within devices. So that's heterogeneity by nature, let's say. There's also heterogeneity by design, which is this idea. You design some instances explicitly to be different, to be heterogeneous, so that you can take advantage of that difference. And let's take a look at what that difference could lead to. Basically, these different instances can be optimized to be more efficient in executing different types of workloads or satisfying different requirements and goals. And these are both valid reasons for designing heterogeneous systems, workloads and different metrics, let's say different goals. Essentially, heterogeneity enables specialization and customization to some degree to both workloads as well as goals. Okay, so these are the two major reasons, in my opinion, why you need asymmetry and heterogeneity in design. Different workloads executing in a system can have different behavior. And the same workload, the same application can have different behavior at different times as well. And systems need to be designed to satisfy different metrics at the same time. And in order to be able to cater for different workloads and different metrics, you want asymmetry. So different applications can have different behavior, obviously. Different execution phase of a single application can have different behavior. The same application executing at different times can have different behavior due to different input sets and dynamic events, user interactions. And there are many, many examples of this. Locality is heterogeneous, predictability of branches is heterogeneous, parallelism is heterogeneous, data dependencies are heterogeneous. As we will see, serial fraction in a parallel program are heterogeneous, bottlenecks are quite heterogeneous. And we have seen that interference characteristics across applications are quite heterogeneous as well. So this is very dynamic as well as heterogeneous in the end. So if you look at the second point, there's almost never a single goal in design. In fact, you can remove that almost. Depending on design points, you have multiple designs, multiple goals, and you have a priority across those goals, of course, right? Usually you have a priority saying performance is the highest goal for me. Energy is second highest, for example, or maybe they're equal somehow. Basically, but there's almost never a single goal. Functionality, reliability is a goal also, even though they may not be implicitly stated in many cases. And you can see there are many metrics, right? Performance, energy, fairness, predictability, reliability. I'm not going to read all of these, but you can have resource level metrics as well as system level metrics. So the problem is, if you do a symmetric design assumes that you have this one size fits all, right? It tries to fit a single size design to all workloads and metrics. This is like a single size shirt, right? You have a t-shirt that you want to buy. They basically advertised as like a fixed size and everybody can wear it. But you know that it's not going to be possible that everybody can wear it, right? Because everybody's different, right? So symmetric design is like that. It's very difficult to come up with a single design, basically. Some people who are going to wear that t-shirt will have a lot of space in the t-shirt. Some people who wear that t-shirt will not have any space in the t-shirt. They will not be able to wear it, right? So it's the same thing, basically, in this case. It's very difficult to come up with a design that satisfies all workloads, even for a single metric. We're talking about even a single metric right now. Even for performance, you cannot satisfy the demands of all workloads if you're symmetric. And if you add multiple metrics at the same time, it's very difficult to come up with a single design that's symmetric that satisfies all design metrics at the same time. And this holds true for different system components or resources. And we've discussed several system components so far: cores, caches, memory, controls, interconnect, disk, servers, as well as I would also consider power and energy resources, thermals as resources, algorithms and policies as well. And I think I like thinking things of pictorially. And if you look at a symmetric design, it looks like this. Whatever resources this may be, C may be cores, for example, in this case. If you look at these symmetric resources, energy and performance is suboptimal for different workload behaviors over here. It's one size fits all. If your workload demands a core that's more powerful than this little core over here, too bad, you don't get it. If your workload doesn't want the inefficiency of the small core, too bad, you'll be inefficient, right? That's the idea. Whereas if you're asymmetric, you enable choice, basically. It looks like this. You have different types of cores in this case, or different types of resources. And you enable customization and adaptation. Because processing requirements vary across workloads, applications, and phases, now you can decide to execute the code on the best fit resources, minimal energy, adequate performance. And the best fit resource is now flexible. If your computation demands a powerful core, you execute the computation on C1. If your computation doesn't demand a powerful core, you choose one of the C5s to execute the computation, right? If it's medium, you choose one of the C2s. Now, asymmetric can be nice if it's configurable also, right? If you can somehow configure the symmetric one to become asymmetric, that could be good also, right? Basically, symmetric, rigid symmetric is not good. Configurable symmetric may be essentially okay because at least asymmetric in the end, right? So configurability or reconfigurability helps asymmetry because fundamentally configurable or reconfigurable systems are asymmetric systems, or you can create asymmetry using configurability or reconfigurability. And clearly we have seen examples before. I'm going to remind you of some of these. In digital design and computer architecture, for example, we've said Cray-1 design, the fastest supercomputer of its time, was not a completely vector computer. Vector computation was important. That's how you do matrix multiplication, for example, right? But it had the fastest scalar pipeline of its time. Why? Because scalar part was the bottleneck in computation. So it was a heterogeneous design. Modern processors have scalar instructions and SIMD instructions. Decoupled access execute that we discussed in digital design. You have a separate access and execute processors. These are examples of heterogeneity. We've seen thread cluster memory scheduling, different memory scheduling policies for different thread clusters. We've seen the idea of radar, heterogeneous refresh rates in DRAM. We've seen heterogeneous latency DRAM, different examples of it. Tiered latency DRAM was one example, but exploiting process variation also was another example, right? Hybrid memory systems that we just discussed is a clear example of this. And there are many types of hybrid memory systems that we discussed also, including for different metrics, right? Performance, endurance, as well as reliability and cost, as we discussed, right? And there are also heterogeneous cache replacement policies that employ multiple different cache replacement policies together. For example, least recently used and random, or memory level parallelism array policies. And this is just to jog your memory if you took digital design and computer architecture. If you look at Cray1, even heterogeneity is a very old idea, as you can see, and it's been employed in systems. You can see that there are vector units and there are scalar units. And even in vector units, there are floating point units and integer units, right? So these are different. And access parts are different from execute parts also, even in Cray1. Okay, hybrid memory systems we talked about. Remember thread cluster memory scheduling, different policies we talked about. I'm not going to talk about that again since we talked about it multiple times. Heterogeneous refresh rates, another example. Heterogeneous latency memory, tiered latency DRAM, as we discussed, is another example, right? You get the best of multiple metrics as much as possible. I'm going through this relatively quickly since we've discussed all of these in earlier lectures, but you get small area and low latency at the same time in this case, right? But you need to manage it because it's heterogeneous. So heterogeneous systems always require management, basically, as you can see in the example of tiered latency DRAM, as we have seen it. As we have seen also in thread cluster memory scheduling, right? You need management in terms of deciding which threads should be treated how in terms of different policies. This is something you have not seen perhaps, but we have heterogeneous interconnects also. Later in the course, we will try to discuss interconnects in more detail. But this is an example multi-core system, a very embedded multi-core system in Tilera. You have 5 different networks. 4 of them are packet switched. 1 of them is circuit switched. So these are different types of operation also. And some of them handle cache requests. Some of them, one network handles cache requests, one network handles cache responses, one network handles IO requests, one network handles core-to-core messaging, and the circuit switch network handles streaming data from one place to another place, one node to another node. And these are designed to be heterogeneous so that they can cater to different types of requests without interference between different requests, right? That's the idea, basically. You can customize the design of a network to different requests that are flowing through the network as well. So basically, heterogeneity is everywhere in the systems we design today, maybe not to the extreme extents that we're going to see in the future, but it's everywhere. And in all resources, it makes sense because different workloads have different requirements from the resources, and resources need to cater for different metrics as well. And also, this is very natural, I think. As we have discussed in the past, heterogeneity is abundant in life, both in nature and human-made components. Humans are clearly heterogeneous, right? We have genetic diversity. It's called genetic variation. And we have a lot of variation. No two human is exactly the same. Even if their genetic diversity is the same, then their interactions with the nature is not the same. As a result, for example, people who are completely the same in terms of their genetic material turn out to be very different in terms of human beings when you interact with them. For example, twins are like that, right? Cells are heterogeneous. They're specialized for different tasks. Organs are heterogeneous. So I'm giving a lot of examples from biology over here, but these are clearly our brain is very heterogeneous, right? As we discussed in the past, it's specialized for different tasks. Cars are very heterogeneous today, right? We design extreme different cars. We don't have a one-size-fits-all car for everyone. So it doesn't make sense to design processors to be one-size-fits-all also. Buildings are heterogeneous. Wherever you're sitting right now is very different. Rooms are heterogeneous, etc. So I can keep going, but it becomes a little boring after this. But it's good to realize it, I think, that everything in life is heterogeneous also. And there's a reason for that heterogeneity. Okay, so one thing I will mention, I think, is general purpose versus special purpose. We've been talking about general purpose, special purpose. I also talked about it in the last lecture or last part of this lecture as well, right? General purpose clearly is tries to do computation, tries to accomplish any computation, right? But it's not good. It's not extremely good at every computation, right? Special purpose is something that's designed specifically for a particular type of computation workload. For example, only thing you can do is execute neural networks, right? Only thing you can do is factor numbers, for example, factor numbers at polynomial time, right? That sounds good, right? But these two things are very different, right? General purpose can do everything. Special purpose can do one task extremely efficiently. General purpose may not be good at doing every task extremely efficiently, clearly, right? Or it may not be able to do some tasks, where it may be able to do some tasks extremely inefficiently, right? It's so inefficiently that we don't want to do it with general purpose machines, right? So asymmetry is a way of enabling specialization, enabling the special purpose system in a general purpose substrate, let's say. So it bridges the gap between purely general purpose and purely special purpose. As I said, purely general purpose has a single design for every workload, every metric. You can throw any workload, past or present or future, and it's going to work okay on this general purpose system. Okay meaning okay in any metric, right? Whereas purely special purpose is designed for single design per workload or metric, and usually a combination of workload and metric in general. For example, very efficient neural network computation, right? Asymmetric is multiple sub-designs optimized for sets of workloads and metrics and that are and glued together. So it bridges the gap in a nice manner, in my opinion. As a result, it gets the best of both general purpose and special purpose worlds. So today's system designs, I'll show you a picture of Apple M1 again, for example. You have different types of accelerators over there. Those accelerators are special purpose. So some of them are purely special purpose, but they're glued into a general purpose substrate, right? Basically, that's what asymmetry and heterogeneity is. Okay, so the goal of a good asymmetric design is to get the best of both general purpose and special purpose, in my opinion, as much as possible. And ideally, you will get the best of any special purpose mechanism as well. Okay, so let's talk about asymmetry advantages and disadvantages. These are general advantages of asymmetric designs over symmetric design. Clearly, you can enable optimization of multiple metrics with asymmetry. You can enable better adaptation of to workload behavior. You can provide special purpose benefits with general purpose usability and flexibility, hopefully. But there are downsides also. Clearly, there's higher overhead and more complexity in design and verification because you have more components. In symmetric design, you have a single component, you stamp it out. In heterogeneous design, unfortunately, you don't have that luxury. You have to design each component, each heterogeneous component, and then glue them together. And you have, as a result, because these things are different from each other, you have higher overhead in management. Scheduling onto asymmetric components is not easy, as we have discussed with hybrid memories, for example, right? We've seen this very well in hybrid memories. If asymmetry is very high between the two different components, managing even multiple metrics across the different components is not easy. And there's clearly overhead in switching between multiple components that leads to degradation. And we have seen this in hybrid memories also. Whenever you move data from one memory type to another memory type, you incur overhead in terms of bandwidth consumption and also cache capacity, right? So let me give you another example. And we've seen this also. Modern processors integrate general purpose cores and GPUs, right? So we have CPU, GPU systems. And this leads to heterogeneity in execution models and ISAs as well. So it's not just heterogeneity in microarchitecture, like we've been discussing so far, but it's also heterogeneity in execution models. The CPU and GPU are programmed in multiple different ways. Add hardware accelerators on top of it, the machine learning accelerators. They have potentially other execution models and ISAs. Now we have actually a collection of different execution models and ISAs in a general purpose substrate, and you need to make them work together. And it's good to contrast it with heterogeneity in only microarchitecture, where you have a single execution model and single ISA, and then you handle the heterogeneity in the microarchitecture without exposing to programmer. But today's systems and going forward, we will have both heterogeneity in microarchitecture, as well as we already have heterogeneity in execution models and ISAs. So we have both today, actually, in today's systems. So the question becomes how to actually take advantage of it. And I think heterogeneity can enable solving of many key problems in future systems. So this is one example I've covered based on what we have covered so far. Clearly, memory system is a big problem. Energy is a big problem because it limits our scalability. And energy, well, efficiency is a big problem, but efficiency is a combination of both performance and energy, and it limits our scalability. And predictability and robustness are big problems also. And clearly, we've discussed these problems, so I'm not going to go through the importance of these. But one thing I will mention is efficiency enables more scalable systems. It can enable new applications. And more efficient systems enable better user experience, so it can enable new usage models as well. So these can enable new platforms too. And we've discussed predictability and robustness, so I'm not going to talk about that. So these are clearly three key future problems, and asymmetric designs can help solve these problems. We've seen examples of this in our past lectures. So in today's and tomorrow's lectures, we're especially going to focus on performance and energy, especially in computation. Can we basically design much more efficient systems that can be much more scalable going into the future by executing some difficult computations much more efficiently? And hopefully these will enable more scalable systems and better user experience as well. Okay, I'm going to talk about these, but before that, I will give you some more examples. This may be an old slide actually, but clearly we have integrated CPU and GPU systems. Some of the earliest ones are Intel Sandy Bridge, a CPU with many hardware accelerators and SoC, like your cell phone. Heterogeneous multi-core systems already exist. CPU plus FPGA systems already exist. So there are many examples. So commercially, this is already happening as well. And commercially, this is going to increasingly happen. Basically, we'll have increasing heterogeneity in the agents, which is computation components, heterogeneous memories, some of which will do computation as well, and heterogeneous interconnects. So I think all of our components are going to be heterogeneous, if not already heterogeneous. If they're already heterogeneous, the level of heterogeneity is going to increase in these components. So clearly, this is not easy to program, because programming, managing these resources for both computation, communication, and storage and memory is not easy. And we need to find good ways of managing these resources. But this is a huge opportunity for scalability and parallelism, because we have a lot of parallelism potential across all of these resources, whether they are CPU, whether they are computation resources or interconnect resources or memory resources. And again, memory resources can be computation resources as well. Keep that in mind. Some of these memory resources are also accelerators, right? Hardware accelerators, as we discussed in the last lecture. And again, just to put an example into the picture, I like picking on Apple's M1 processor because it's a very nice example. As you can see, we already have high performance and efficient cores, two different types of cores, GPUs, neural engines, and some of the things that are not discussed also in this, some other accelerators. So clearly, heterogeneity is everywhere in our systems today. Let me give you a historical perspective as well, because multi-core systems, when they started, were not heterogeneous. So I think it's good to think about this, let's say, dichotomy between large cores and small cores, and think about where people have landed. Because this is actually this, let me show you, this idea of putting CPUs and GPUs together and putting multiple different types of cores in the same substrate is not a new idea. It's been done in recent processors, and that's good because that's a step in the right direction. But this is an idea that dates back as early as 2002 or so. When multi-core systems were designed, actually, they were designed as symmetric cores. Basically, there was a good reason for them. People were having difficulty scaling a single core. So they wanted to put simpler and lower power cores than a single core and have many of them on a single chip so that they can enable large scale parallelism. But they started putting different types of cores. So you can see that these are different multi-core systems. Some of these are extremely small cores over here. These are examples over here. Well, GPUs also have cores. Whatever they call are debatable. They call cores is debatable, of course, but they have some sort of cores also, right? And these are also small cores. So ideally, what you want, you've seen the slide before. You want n times the performance with n times the cores when you parallelize an application on n cores, right? So we're talking about parallelizing an application, a single application right now, not multiple applications. What we get today is Amdahl's law. Basically, we have a serial bottleneck. We're going to talk a lot about Amdahl's law going forward. How many people know about Amdahl's law? Just to see a show of hands. So some people. How many people do not know about Amdahl's law? Okay, that's good. That's good. Then you have not taken digital design and computer architecture probably, or maybe you don't remember it from there, but that's fine. But Amdahl's law, it says that there's a serial bottleneck in programs that limits how much you can parallelize a program. And clearly it's a function of your algorithm as well as your program design. And we're going to talk about that. But we also get bottlenecks in the parallel portion also. Even if you parallelize your program, the parallel portion is not perfectly parallel. So assume that Amdahl's law doesn't exist. You got rid of all of your serial bottleneck. There's still bottlenecks in your parallel portion. And we've discussed some of them, actually. I'm going to discuss more of them. So, okay, let's talk about Amdahl's law. We're going to see this more in multiprocessors again as well. But basically, Amdahl's law states very simply that you have a parallelizable fraction of a program and you have a non-parallelizable part. Parallelizable fraction is explained as f, and non-parallelizable part is 1 minus f. Okay, and it's introduced in this seminal paper by Gene Amdahl, who was actually the chief architect of IBM's 360 line of processors. And basically, in this paper, he argued that there are some workloads that we cannot parallelize. As a result, the capability of multiprocessors is very limited. So single processor, we should still keep improving single processor performance. So what does Amdahl's law state? Amdahl's law state that, let's assume that you have n number of processors. Parallelizable fraction of the program reduces to f over n in terms of, let's say, execution time. And non-parallelizable fraction, you cannot do much about it, basically. So a parallelizable fraction goes down to f over n because it's perfectly parallelizable. Non-parallelizable portion stays at 1 minus f. As a result, speed up with n processor becomes this equation. Does that make sense? So a parallelizable fraction speeds up by n. Non-parallelizable fraction doesn't speed up at all. As a result, speed up equation looks like this. And that's the speed up with n processors. And maximum speed up is limited by that number f right now. So if f is, let's say, 50%, parallelizable portion is 50%, this number over here becomes 0.5, right? This number over here becomes 0 as n goes to infinity, because we're thinking perfect parallelization, right? As n goes to infinity, the parallelizable fraction of the program becomes non-existent in terms of execution time. So you're bottlenecked by the non-parallelizable portion, meaning that if n, even if you have infinite number of processors, if f is 0.5, you get only a speed up of 2. That doesn't sound very good, right? An infinite number of processors and I get a speed up of 2. That's not good. I should really improve my parallelizable fraction. Right? Even if you have a parallelizable fraction of 90%, 0.9, your speed up, your maximum speed up achievable is 10. Even if you throw an infinite number of processors to the problem. So basically, that's how important the serial bottleneck is. Even if the serial bottleneck is 0.01%, your maximum speed up is 100x, right? 100. 100 is nothing compared to infinite number of processors, right? You're very much bottlenecked, basically. Unless you make the parallelizable portion 100%, you still have Amdahl's law. Okay, but parallel portion is also usually not perfectly parallel, as we have discussed, right? You have synchronization overhead, meaning you have updates to shared data. So you have locking mechanisms. As a result, not all threads can be executing in parallel at any given time. Even though you're in a parallel portion, some thread may be updating some shared data, right? We discussed this earlier when we talked about parallel application memory scheduling. We're going to discuss this even more. Load imbalanced overhead. Parallelization may not be perfect. So some threads may have more work, some threads may have less work. Remember the example I gave from threads counting the characters in a book, and you partition the book such that each thread gets 100 pages. The thread that got 100 pages of figures has nothing to do because there are no characters in those, right? As a result, it finishes its work much earlier. As a result, your program is not perfectly parallel. Your parallelizable fraction of the program is not perfectly parallel. So this is very important also. So resource sharing overhead, we've seen contention among processors, right? You have many processors contending for some resource, and one of them has to wait when the other is accessing that resource. We've seen this in memory scheduling, for example. This is present in caches. This is present in hybrid memories, etc. As a result, even though you may think that you parallelize your program and you're executing on multiple different processors nicely, because of interference across different resource, across the same shared resource between different threads, you get delays. And that leads to this f over n being incorrect. Basically, this is not a simple equation like f over n. You need to take into account the bottlenecks in the parallel portion as well. Okay, so hopefully that's interesting. We're going to talk about basically how to speed up the serial bottleneck as well as this parallel bottlenecks in today's remaining part as well as tomorrow's lecture. So basically, the problem is many parallel programs cannot be parallelized completely. As we discussed, there are sequential, there are serialized code sections. Sequential code portions are an extreme example. This is Amdahl's serial bottleneck, but there are critical sections, there are barriers, and there are limiter stages in pipeline programs that we have discussed in an earlier lecture as well. We're going to discuss more. And these serialized code sections reduce performance, limit scalability, as well as waste energy. Because you basically, let's say you dedicate one thread, and the thread has nothing to do in the core, and the core is basically waiting for other cores to finish, right? It limits scalability because you're not utilizing your cores well. It's wasting energy. It's reducing your performance. It's doing everything that I discussed over here. Let me give you one example. MySQL is a commonly used database, open source database. It's actually being improved by many database companies also. Basically, in MySQL, a thread opens the database tables, and then it performs operations on the tables, rows and columns it opens, basically. Performing operations in parallel because you get the lock on the database table, so you can parallelize the operations. But opening the database tables requires access to open tables cache, which is a shared data structure. And it turns out you need a critical section to access this. And this is what your performance looks like if you have a symmetric cores. Basically, you have some number of cores going from 1 to 32 in this particular case, symmetric cores. And this is what your speed up looks like. Basically, going from 1 to, let's say, 15 or 16 cores over here, you get good speed up, 6x. It's not perfect, right? Ideally, I would expect going from 1 to 16 cores, I would expect 16x speed up, but I'm getting 6, which is still better than getting less. So clearly there are some bottlenecks in the parallel portion, which is critical sections, for example. That's one example. Interference, resource sharing, cache coherence overheads are other examples. But there's something interesting happening. As you keep adding more cores and more threads, your performance starts reducing now, meaning your speed up starts reducing. This is speed up compared to a single core execution, single thread execution. It maximizes over here. It starts reducing over here. Now your overheads are too high. Why? Some of this are contention overheads because cache coherence overheads, because the data that you need to access, the locking that you need to do for the critical section, the lock is traveling between the caches. Some of it is memory bandwidth bottlenecks, potentially. Some of it is other interference issues that you have. They're basically reducing your performance because you basically overloaded your system with too many threads, and the overheads are too much, basically. The parallelism, additional parallelism is not overcoming the overheads that are in the system. Okay, so this is symmetric. But today, with a symmetric system, you can actually make it much better. And we will see an example of a symmetric system where we have asymmetric multi-core, and we execute these critical sections on a large core that is able to execute these critical sections fast. So hopefully that'll be interesting. But we will probably get to it tomorrow. So asymmetric designs can enable better scalability. I think this is called a scalability curve. Basically, it shows that how much your performance scales with the number of threads or chip area, number of cores, basically. Ideally, you want linear scaling, right? As we will see in our multiprocessors lecture, linear scaling is the best. If you have super linear scaling, then probably you're doing something wrong, meaning you either have an unfair comparison or you're adding more resources than just cores. But you usually get curves that look like this. For both of these actually are reasonable curves that you can see today. Usually the scaling is sublinear with number of cores. But ideally, you would like to get as linear as possible. Okay, so basically, we have different demands in different code sections. It's good to recognize that. What we want is, in a serialized code section, we want one powerful large core. In a parallel code section, we probably want many wimpy small cores, because parallel code section is extremely parallel. Serialized code section is only one thread is executing, usually, right? In amdahl serial bottleneck, for example. So clearly, these two conflict with each other. If you have a single powerful core, you cannot have many cores. And a small core is much more energy efficient and area efficient than a large core. So you can put many small cores in the same area. Let's take a look at these large versus small cores. Large core has a lot of techniques to exploit parallelism, instruction level parallelism, out of order, white fetch, deeper pipelines, aggressive branch prediction, multiple function lists, trace caches, etc. Small core is very small, basically very wimpy, in order, narrow fetch, shallow pipeline, simple branch predictor, few functional units. And large cores are usually power inefficient. For example, this is a good rule of thumb. You get 2x the performance for 4x the area or power. And this is from this paper from Intel, actually. It's a nice paper. It was published in ICCD in 2004, where they basically show the difference between large and small cores. Basically, large core can be very good at performance. You can see 5 to 8x, but its power consumption is much higher. And its normalized energy per instruction is also much higher. So small cores are actually much more energy efficient, but they're not the highest performance, absolutely, as you can see, right? And I recommend you reading that paper if you're interested. So multi-core evolution happened that way, basically. People decided symmetric cores were good to start with. And IBM Power 4, for example, was one of the first multi-core systems. You can see the paper from 2002. It's actually a beautiful paper that I would recommend you to read. IBM used to write papers about its microarchitectures and system And this is very nice. And you can see that it's essentially two cores, two powerful cores. You can see they're very powerful cores by that type standards. And these are symmetric though. So they could not get the best of both worlds. IBM Power 5 added multi-threading into each of the cores without changing the core structure that much. They're still symmetric cores. On the other hand, people took the exact opposite extreme. Sun Niagara, for example, when Sun was around, they decided to design this multi-core system that are heavily multi-core. They have 8 cores, as you can see, not 2 cores, and each core has 4 threads, so they have 32 threads over here. And each core is very wimpy, very simple core. They basically said, we don't need large cores. We're executing these workloads that don't need large cores, commercial workloads. Well, they should have known better, basically. But basically, this is how simple the cores are. You can see it's very simple. It's fine-grained, multi-threaded, 6-stage, dual issue in order. They even had a shared floating point unit that they fixed in larger incarnations of Niagara. So basically, this doesn't perform well in code sections that demand high performance. So let's take a look at, let's analyze these 2 different cores. What we want is in a serialized code section, one powerful large core, meaning like something like IBM Power 4. In a parallel code section, we want many wimpy small cores, something like Sun Niagara. But we cannot get the best of both worlds because these 2 conflict with each other, as we discussed, right? The question is, can we get the best of both worlds? Let's take a look at, let's do some quick analyses, basically. Assume that small core takes an area budget of 1 and has performance of 1, and a large core takes an area budget of 4 and has performance of 2. This is what we'll assume. Tile large approach looks like IBM Power 4, Power 5, and AMD and Intel took initially, but later they became heterogeneous, of course. So you get high performance on single thread serial code sections. So you get 2 units of performance based on the equation that I showed you. But you get low throughput on parallel program portions. You get 8 units, as you can see, because each of them gives you 2 units, and you have 4 of them. 4 times 2 is 8. Tile small, it gets high throughput. This is similar to some like Tylera Tile and Sun Niagara. Intel Larrabee was another example. None of these were extremely successful, let's say, because they actually reduced performance compared to large cores. But you get very high throughput on the parallel part, 16 units, but you get low performance on the serial part. Your performance even reduces compared to a large core, basically, 1 unit. So basically, Tile large is good for high performance on single threads, but low throughput. Tile small is high throughput, but it has low performance on single thread serial part. In fact, if you go from Tile large to Tile small, large core to small core, you lose market potentially, as has happened to some of these companies, because you reduce your single thread performance. And people do need single thread performance in cases where that single thread performance is critical. And there are many cases where that is true, as we will also see tomorrow. And the idea in asymmetric multi-core is have both large and small on the same chip. And this is performance asymmetry, basically. And that's what brings us to asymmetric multi-core. And this is what it looks like, basically. You have a large core. And this is just one example, right? You can have 1 large core, 12 small cores in this particular case. You can extract the serial parts, the difficult to code sections, and get the performance of 2 units. And you can execute the parallel part on small cores as well as the large core so that you can get high throughput. You get 12 throughput over here, plus 2 in the large core. You get 14 units. But if you make large core multi-threaded, you can easily get to 16 as well. So hopefully these calculations are interesting. So now you can actually have extract serial bottlenecks. You can have whenever you have single thread, you execute on the large core. Whenever you have multiple threads, you distribute them to smaller cores. So the parallel portion of the program can execute on the small cores, whereas serial portion of the program can execute on the large cores. And this is where accelerating the serial bottlenecks can come into play. Now, if you actually do the performance versus parallelism assumptions, again, this is what the equation looks like. I've already given you, actually. But when you Tile large, this is very good for serial performance. You get 2, not good for parallel throughput. When you Tile small, great for parallel throughput, but not good for serial performance. Asymmetric multi-core tries to achieve the best of both worlds. Good for serial performance, good for parallel throughput, and it can be better if you actually make the large core multi-threaded. Now you could argue that Tile large can also make the large core multi-threaded. Yes, absolutely. So if you make the large cores more customizable, configurable, sure, you can actually get higher throughput, parallel throughput as well. So basically, if you modify Amdahl's law for an asymmetric multiprocessor, it starts looking like this. It's a bit more complicated, but now this is simplified Amdahl's law for an asymmetric multi-core processor. serial portions execute on the large core, parallel portions execute on both small and large cores. F is still the parallelizable fraction of the program. L is the number of large processors. S is the number of small processors. X is the speed up of a large processor over a small one. Now, your serial fraction also gets accelerated by X, right? Because the base processor is a small processor. Your serial fraction executes by 1 minus F gets divided by X because you're executing on a large core, not all small cores. Your parallel fraction gets executed on small cores plus one large core. And one large core's benefit is X times L because it's higher performance than a small core. So you can do these equations, plug these numbers yourself if you're interested. And if you basically, if you do this, you can get rid of some of the serial bottlenecks because your serial bottleneck now, your serial bottleneck now executes on the large core, but you can potentially execute these parallel portions, bottlenecks in the parallel portion, also in the large core, and take advantage of this equation by executing those bottlenecked parts in the parallel portion over here. And in the next lecture, we're going to see examples of how we can actually execute bottlenecks in the parallel portion in the large core so that we can speed up multi-threaded programs significantly. Okay. Any questions? Yes, there's one question. Please go ahead.
Does the study take into account multi-programming workloads? If you had multiple applications, wouldn't it be worse if you decrease the number of large cores? Mm-hmm. And if you have multiple applications that then contend, and one application gets, well, mm-hmm. some applications get the large cores and many applications get the small cores, wouldn't that make performance worse?
Yeah, so that's an excellent question, basically. I mean, here I just give an example of one large core, but I think to scale up the system, you really need multiple large cores and many small cores, just like what's happening in industry today. So you're absolutely right. Having one large core is not enough, really, for a scalable system when you want multi-program workloads. But in this lecture and the next lecture, most of next lecture, not all of next lecture, we're going to talk about a single workload and how to manage heterogeneity for a single multi-threaded workload. But your point is absolutely crucial. If you have multiple workloads, we're going to talk about how to manage multiple workloads also. But if you have multiple workloads, having multiple different large cores is actually extremely important. Okay. Yes, there's another question. If there's no one contending for the room, we can continue, I think, with questions. You're the ones who are seeing it, but go ahead.
Is the main cost, I mean, is the reason for the inefficiency that clocking your core faster is just not that scalable? So it costs a lot more energy to make it twice as fast? Yeah, so that's a good question also. Basically, I think what you're saying is, why not clock these small cores to be faster, right? You can do that, yes, but it's energy inefficient. And also, you don't get all the benefits of the large core, basically. Because large core provides benefit more than just frequency, right? It's all of these microarchitectural instruction per cycle improving techniques. Like you have large caches, for example. You have out-of-order execution, heavy levels of out-of-order execution. So you get benefits from that as well. But yes, if you do the equation in terms of energy, these should be perhaps energy neutral as well. And clocking all of these small cores to be extremely high frequency is not going to work very well because it's going to go against your power budget. Oh yeah, I think I was just trying to answer my mind. Like I got sort of inconsistent or like a difference between memory and computation, because in memory it seems like the reason why we wanted to increase capacity rather than stack 100 separate sticks of RAM together is because you get better energy efficiency when you try to fit more into one chip. But for computation, it seems like it's the opposite. When you try to fit more into one chip, you actually lose your efficiency. So I guess, yeah.
Well, I think I'm not entirely convinced about the efficiency argument that you make. I think still, for example, you can have a lot of small cores, and you can run them relatively slow, but because of the parallelism, you can get a lot of efficiency, right? So lowering the frequency can actually make you much more energy efficient by packing many small cores over here, as long as you can parallelize your program extremely well. Does that make sense?
I think so.
Okay.
And I guess just a question about the I guess, the earlier part of the lecture on symmetry.
Sure.
Would you say, like, which mindset would you agree with more? To design things, trying to respect symmetry until it makes no sense to do so, and it should be heterogeneous, or to have heterogeneous as the default mindset, and then continue with that until it doesn't make any more sense to deal with the overheads.
Yeah, so that's I mean, that's also a good question, right? I mean, I think it needs to be examined in any design that you are looking at, right? So if you're looking at a computer system design, I mean, certainly symmetry has benefits, but again, if you're not achieving your goals on efficiency and performance, I think heterogeneity can be the default also, right? I think in today's systems, probably the mindset should be heterogeneity from default, because we have kind of exhausted the limits of symmetry, and with heterogeneity we can make things much more efficient by building accelerators in our systems. But again, if you take this to the extreme, it may not be wieldy as well, right? You don't want to build an accelerator for every single program out in the world, right? So it becomes a balancing act at some point, right? How do you classify subsets of workloads that are important enough so that you can design asymmetry into your system to cater to those workloads? But I would argue today's systems, the mindset has to be heterogeneous. Maybe that was not the case 20 years ago.
That makes sense. Thank you.
Sure. Okay, very good questions. It doesn't look like anyone is taking over the room, but we should stop regardless. So I think tomorrow we're going to start from here. Basically, maybe I'll briefly mention the slide also. But basically, I've already said this. What I said was we would like to identify critical parts of a program, dynamically identify them, dynamically identify those critical parts of a program that cause serialization and execute them on a large core. And this is a mindset. Executing them on a large core is just one example of accelerating them. You can come up with other ways of accelerating them, right? We have seen, for example, parallel application memory scheduling. But we will see how to identify these different code portions and also how to accelerate them and what goes into the challenges of this sort of bottleneck acceleration. But you can also free your mind and think critically and say, oh, there may be other ways of accelerating these important pieces of code, and depending on their bottlenecks, of course. Okay, so I will stop. Thanks for asking a lot of questions, even though we had to be remote. Tomorrow, I think we will still be remote, even though I'm feeling better. After lecturing, I feel a bit better, but I don't know how it will continue toward the day. But to protect everyone, I think we will still be remote tomorrow, and we will continue with bottleneck acceleration. Okay, take care. Have a good evening.